Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. There's a part of us that's always been obsessed with finding the biggest thing. The highest mountain, the largest ocean. But what about the biggest galaxy? For decades, the undisputed king of the cosmos was a galaxy called IC 1101, a monster so vast it could swallow our own Milky Way hundreds of times over, a city of maybe 100 trillion stars. For about 40 years, we thought nothing could ever come close. But then, in 2022, astronomers found something new. Something that doesn't play by the same rules. A structure so enormous, it forces us to rethink what a galaxy can even be. And it begs the question, what is the largest galaxy we've ever observed? The answer is more complicated, and way more fascinating, than you might think. It makes us question what largest even means. In doing so, it reveals a universe that is far stranger and more magnificent than we ever imagined. We're going to break it down, slowly, piece by fascinating piece, to understand not just the what, but the why and the how. The primal urge to measure the universe. Before we jump billions of light years into the cosmic dark, let's start with a question that's a lot closer to home. Why do we even care? Why are we so captivated by the idea of the biggest? This isn't just a trivial chase for a new headline or record book entry. It's a fundamental part of what makes us human, a deep-seated drive that has pushed us from our earliest days. Imagine our distant ancestors on a savanna, scanning the horizon. Their survival depended on understanding their environment. Which mountain was the highest, offering the best view? Which river was the longest, a reliable source of water? Which predator was the biggest, posing the greatest threat? Mapping the extremes of their world wasn't a hobby, it was a critical tool for survival. It allowed them to build a mental map of their reality, to understand its boundaries, and to find their way through the chaos of the natural world. These extremes were like anchors, fixed points in a world of constant change. That ancient wiring hasn't gone away. It's just scaled up. We've traded mountains for gas giants, rivers for stellar nurseries, and apex predators for supermassive black holes. Our tools have evolved from sharp rocks and keen eyes to robotic probes and continent-spanning radio telescopes, but the curiosity underneath it all is the same. When we look up at the night sky, we are still that early human, trying to make sense of the vast, intimidating wilderness all around us. Psychologically, our fascination with cosmic superlatives, the biggest, the oldest, the farthest, is about trying to wrap our minds around the sheer awe of it all and find our place. The universe is, by its very nature, incomprehensible. Its scales of time and distance are so far removed from our daily lives that they can make you feel dizzy, small, and insignificant. But by finding and labeling the extremes, we create a framework. We build a ladder of scale. Knowing that the star Betelgeuse is so large it would swallow Jupiter's orbit doesn't just tell us about Betelgeuse, it gives us a new way to understand the size of our own sun. Knowing that there are galaxies millions of light years across gives us a new appreciation for the 100,000 light-year span of our Milky Way. These records aren't just cosmic trivia, they are the benchmarks we measure our own existence against. This quest for the biggest is also what fuels the engine of discovery. It pushes our technology to its limits and forces us to ask new, deeper questions. The search for the largest galaxy isn't just about finding a bigger object, it's about stumbling upon physical processes and cosmic environments we never knew were possible. It leads us to question our basic models of how galaxies form, grow, and die. It's at the extremes, at the very edge of what we thought was possible, that our most cherished theories get tested and, sometimes, broken. And in that breaking, a new, more complete picture of the universe starts to come together. So, as we head out on this journey to find the largest galaxy, remember that we're doing more than just sightseeing. We're following an ancient impulse, one that connects us to our earliest ancestors. We're trying to map the cosmos, to find its anchors, and in doing so, to better understand our own small, but not insignificant, place within it. The question, what is the largest galaxy, isn't just about the answer, it's about the very human need to ask it in the first place. Defining largest, a cosmic measuring tape. Before we can crown a champion, we need to agree on the rules. And when it comes to measuring galaxies, the rules are surprisingly slippery. The question, what is the largest galaxy, sounds simple, but in cosmology, the simple questions often hide the deepest secrets. A galaxy isn't a solid object with a neat edge like a bowling ball. It's a sprawling, messy, and ghostly collection of different parts, and you could use any of them to define its size. First, and most intuitively, we could measure a galaxy by its asterisk stellar extent. This is what most people think of. We look at a galaxy and measure how far its visible light, the light from its stars, stretches across the sky. Astronomers often do this by tracing a line where the galaxy's light dims to a certain faintness and calling that its edge. This gives us a picture of the main body of the galaxy. For a long time, this was the standard way to measure a galaxy's size. It tells you about the galaxy's most familiar ingredient, its stars. But even this gets fuzzy. The outermost stars of a galaxy form a huge, incredibly faint halo that just sort of fades into the blackness of space. Where do you decide the galaxy ends and the void begins? That line in the sand is a choice made by astronomers, not a true physical boundary. Then, things get even weirder. At the heart of most large galaxies lie supermassive black holes, engines that can dramatically reshape their entire environment. These black holes are messy eaters. As they pull in gas and dust, not all of it falls in. Some of this material gets superheated into a plasma and funneled by intense magnetic fields into two colossal jets, which are blasted out in opposite directions at nearly the speed of light. These jets travel for millions of years, pushing aside the thin gas between galaxies until they slow down and billow out into enormous, mushroom-shaped clouds. These are called asterisk radio lobes. They're completely invisible to the naked eye and even to optical telescopes like Hubble. They don't shine with starlight, they glow in radio waves. This happens as energetic electrons spiral around magnetic field lines, a process called synchrotron emission. So, a new question comes up: should these radio lobes count as part of the galaxy? They are, after all, material shot out from the galaxy's own central engine. They represent the true sphere of influence of the black hole. If we include them, our definition of largest changes dramatically. A galaxy that looks pretty normal in visible light could suddenly become the biggest thing for millions of light years when seen with a radio telescope. And to complicate things even more, there's the dark matter halo. We know from the way galaxies spin that the stars and gas we can see are just the tip of the iceberg. The vast majority of a galaxy's mass, maybe up to 85%, is made of a mysterious, invisible substance called dark matter. This dark matter forms a gigantic, spherical halo that stretches far beyond the visible stars. This halo is the true gravitational anchor of the galaxy. It decided how the galaxy formed in the first place. If we were to define largest by the full reach of a galaxy's gravity, then we'd have to measure the size of this dark matter halo. But how do you measure something that's invisible? We can only guess its size indirectly, by looking at its gravitational effects on the things we can see. So, you see the problem. There's no single, easy answer to how big is a galaxy. Is it the size of its stellar disk, the part we see in pretty pictures? Is it the full reach of its radio lobes, those ghostly arms stretching across the void? Or is it the invisible shroud of its dark matter halo, the true measure of its gravitational kingdom? The answer is, it depends on what you want to measure. Are you interested in where the stars live? Or are you interested in the galaxy's total influence on the universe around it? This isn't a failure of astronomy, it's a reflection of the beautiful complexity of the cosmos. And it sets the stage perfectly for the story of our two main contenders. One is a champion of the visible, a king of stars. The other is a titan of the invisible, a master of radio waves. Act 1. The reign of IC 1101, the visible giant. For the better part of half a century, if you asked an astronomer to name the largest known galaxy, the answer would have come back fast: IC 1101. For decades, this galaxy was the undisputed heavyweight champion of the cosmos. Discovered on June 19, 1790, by the legendary astronomer William Herschel, IC 1101 was at first just another faint, fuzzy spot in his telescope. In Herschel's time, no one knew what galaxies really were. They were thought to be clouds of gas inside our own Milky Way. It took another 130 years before Edwin Hubble proved these spiral nebulae were actually distant, island universes. And only then did we start to realize the true nature of what Herschel had found. IC 1101 wasn't just another galaxy, it was a monster. Located about 1 billion light-years from Earth, at the heart of a dense galaxy cluster called Abell 2029, IC 1101 is the perfect example of a brightest cluster galaxy, or BCG. In the ruthless world of galactic evolution, location is everything. Galaxy clusters are the great cities of the universe, crowded places where thousands of galaxies are all bound together by gravity. The galaxy that ends up at the gravitational center, the one at the bottom of the gravity well, has a massive advantage. It grows by relentlessly eating its neighbors. This is the story of IC 1101. Over billions of years, it has engaged in cosmic cannibalism on an unimaginable scale. One by one, smaller galaxies that strayed too close were torn apart by IC 1101's immense gravity, their stars, gas, and dark matter swallowed up by the growing behemoth. Imagine dozens of galaxies the size of our Milky Way and Andromeda, all merging over cosmic eons. That's how IC 1101 was built. It is a galaxy forged from the wreckage of others. The result is a galaxy of truly staggering proportions, when measured by its stars. Our Milky Way has a respectable diameter of about 100,000 light-years, but IC 1101's main body of stars alone is already much larger. But its true immensity is revealed in its vast, diffuse halo. This is a sphere of stars, stripped from those devoured galaxies, that extends far out into space. While the main body is around 400,000 to 550,000 light-years across, its faint, ghostly halo of light extends to a radius of about 2 million light-years, giving it a total diameter of around 4 million light-years. Let's try to put that in perspective. If you placed one edge of IC 1101's halo where our Milky Way is, the other end would stretch far beyond our nearest major galactic neighbor, the Andromeda Galaxy, which is about 5 million light-years away. It would swallow our entire local group of galaxies with room to spare. The number of stars here is equally mind-boggling. While the Milky Way has a few 100 billion stars, estimates for IC 1101 suggest it has a staggering 100 trillion. Visually, IC 1101 is classified as a supergiant elliptical or lenticular galaxy. Unlike the beautiful, blue-tinged spiral arms of galaxies like our own, which are buzzing with the birth of new stars, IC 1101 has a more settled, golden-yellowish glow. This color tells us it's old. It's mostly populated by ancient, metal-rich stars, some billions of years older than our own sun. Star formation has pretty much stopped. It's run out of the cold gas needed to make new stars. In a way, it's a dying galaxy, a vast, quiet city of ancient suns. But deep within its heart, astronomers have found one of the most massive supermassive black holes ever discovered, a monster weighing as much as 40 to 100 billion suns. Its core is the largest and puffiest known, likely because as black holes from devoured galaxies merged, they violently kicked stars out of the central region. For all these reasons, IC 1101 held the crown for decades. It was the largest known collection of stars in the universe. It seemed unbeatable. How could anything possibly be bigger? Well, the answer was hiding in plain sight, just waiting for us to look at the universe in a completely different light. Act 2. The Challenger, Alcyoneus, the hidden giant. For 40 years, IC 1101's reign seemed untouchable. But science never sits still. Just when we think we have the universe figured out, it throws us a curveball. In February 2022, a team of astronomers led by Martin Oe from the Leiden Observatory announced a discovery that did just that. While digging through data from a huge network of radio telescopes across Europe called LOFAR, they stumbled upon something staggering. It was a structure so mind-bogglingly enormous that it immediately challenged IC 1101's title. They named it Alcyoneus, after a giant from Greek mythology. Alcyoneus is about 3.5 billion light-years from Earth. If you were to look at its host galaxy with a normal telescope, you wouldn't be blown away. It's a fairly standard-looking elliptical galaxy. It's large, sure, but nothing suggests it's a record breaker. Its stellar mass is around 240 billion times that of our Sun, actually less than the Milky Way. Its supermassive black hole is about 400 million solar masses, a beast for sure, but a lightweight compared to the one inside IC 1101. By all visible measures, Alcyoneus is suspiciously ordinary. But the visible light isn't the real story. The real story is what the LOFAR radio telescopes revealed. Extending out from this unassuming galaxy are two of the most colossal structures ever seen, a pair of gigantic radio lobes. These are the ghostly plumes of plasma we talked about earlier, fired from the poles of the central black hole. And in the case of Alcyoneus, they are on a scale that just about breaks your brain. From one end to the other, the radio lobes of Alcyoneus stretch for 5 megaparsecs. That's a staggering **16, 3 million light-years. Let's just pause on that number. It's a distance that's fundamentally impossible to comprehend. The visible disk of our own Milky Way is about 100,000 light-years across. You would need to line up more than 160 Milky Way galaxies, end to end, just to span the full width of this one structure. Remember IC 1101, the old king, with its stellar halo of about 4 million light-years? Alcyoneus is roughly 4 times larger than that. It is, without any serious competition, the largest structure ever created by a single galaxy that we have ever seen. So what are we actually looking at? These lobes aren't made of stars. They are vast, ethereal clouds of super-hot plasma electrons and protons threaded with weak magnetic fields. They were created by powerful jets of particles shot out from the galaxy's black hole millions of years ago. These jets traveled at nearly the speed of light, piercing through the galaxy and deep into the near-empty void of intergalactic space.
Over immense timescales, they pushed back the thin gas that exists between galaxies, inflating these two gigantic bubbles. The lobes we see today are the afterglow of this ancient, violent event. They glow faintly in radio frequencies because the electrons inside are still spiraling around magnetic field lines, broadcasting their presence across billions of light-years. The discovery of Alcyoneus was, in the words of the research team, a stroke of luck. They weren't looking for a new record holder. They were using new image processing techniques to reveal faint, diffuse structures that are often lost in the noise of radio data. And when they did, these two colossal, previously unnoticed plumes emerged. This immediately raised a huge question. Why is Alcyoneus so big? Giant radio galaxies aren't new, but none come even close to this scale. The puzzle only deepens when you look at the host galaxy. As we said, it's not particularly special. It doesn't have an unusually massive black hole, nor does it seem to be producing freakishly powerful jets. So why did its lobes grow to such a monstrous size when others didn't? Astronomers are still debating this, but they have a couple of ideas. One is that Alcyoneus happens to live in a region of space that is significantly less dense than average of vast cosmic void. In this extra empty environment, the jets would have faced less resistance, allowing them to travel much farther and inflate the lobes to a greater size. Another possibility is that the jets are flowing along a filament of the cosmic web. The universe is structured like a gigantic spider web, with long filaments of gas connecting massive galaxy clusters. If Alcyoneus's jets are aligned with one of these filaments, they could be traveling down a pre-existing channel, allowing them to grow to their incredible length. Whatever the reason, the discovery of Alcyoneus completely changed the conversation. It was a dramatic reminder that the universe's most impressive structures might not be the ones that shine the brightest. The true giants could be hiding in the dark, whispering to us in radio waves. The stage was now set for a cosmic showdown, the king of stars versus the behemoth of radio waves. The slowly explained core. A tale of two giants. So, we have our two champions. In one corner, IC 1101, the Old King, a galaxy whose sheer number of stars and vast, glowing halo made it the largest for decades. In the other, Alcyoneus, the new challenger, a seemingly normal galaxy with an invisible secret, radio lobes that stretch across a mind-altering expanse of space. So which one is truly the largest? To answer that, we have to deliver on the promise of our title and explain it slowly, because the answer reveals the very different ways galaxies can dominate the cosmos. This isn't a simple case of one number being bigger than another. It's a tale of two entirely different kinds of bigness. It's like asking whether the Amazon or the Nile is the greatest river. One is much wider and carries more water, while the other is longer. The answer depends on how you measure. It's the same with galaxies. IC 1101's claim to fame is its asterisk mass and stellar population. It is, simply put, the most massive collection of stars we have ever found in one gravitationally bound system. Its size, measured at around 4 million light-years in diameter, is defined by the faint outer glow of its stellar halo, the cloud of stars it has vacuumed up over billions of years of galactic cannibalism. When we measure IC 1101, we're using telescopes that see visible light, the kind of light stars give off. We're essentially taking a photo. This makes IC 1101 the king of the tangible, visible universe. Its size is a direct reflection of its history as the gravitational bully in its crowded neighborhood. It's the heavyweight champion, defined by its substance. Alcyoneus, on the other hand, is the champion of asterisk spatial extent. Its claim isn't based on its stars, which are pretty average. Its record-breaking size of 16.3 million light-years comes from the full reach of its radio lobes. These lobes are incredibly diffuse. While they cover a colossal volume of space, their actual mass is tiny compared to the host galaxy. They're more like an enormous shadow or footprint than a solid object. To measure Alcyoneus, astronomers use radio telescopes like LOFAR, which are blind to starlight but can see the faint radio glow from the plasma in the lobes. So, we have two different ways of measuring, revealing two different kinds of galactic giants. The Hubble telescope, a master of visible light, shows us the stellar empire of IC 1101. LOFAR, a master of radio waves, unveils the breathtaking influence of Alcyoneus. This brings us to the core of the scientific mystery. How do these two different types of giants form? A galaxy like IC 1101 is built through mergers and acquisitions in a dense environment. It's a slow, grinding process of gravitational accumulation. Its growth is external, driven by what it can pull in from its surroundings. A structure like Alcyoneus is made in a completely different way. It's driven not by what's outside, but by an engine inside, the central supermassive black hole. The size of its radiolobes depends on a delicate dance of factors: the power of the jets, how long the jets stay on, and crucially the environment the jets are blasting into. That third point seems to be the key for Alcyoneus. The leading theory is that its host galaxy lives in an exceptionally empty patch of space. Imagine trying to inflate two identical balloons. One you inflate in a swimming pool, and the other in the open air. The balloon in the water will face way more resistance and won't get as big. In the same way, the jets from Alcyoneus may have traveled for millions of years with very little to stop them, letting them inflate these record-breaking lobes. It's possible Alcyoneus isn't firing more powerful jets, but has just been firing them for an exceptionally long time into an exceptionally empty stretch of the universe. So, to summarize the showdown, IC 1101 is the largest known galaxy if you are measuring the physical collection of stars. It is the most massive known stellar system. Alcyoneus is the largest known galactic structure if you are measuring the total spatial footprint of a galaxy's activity. It represents the largest sphere of influence ever documented. The debate over which is truly larger is, in some ways, a matter of opinion. But for most astronomers today, Alcyoneus has taken the title of largest known galaxy, simply because its 16.3 million light-year measurement represents the largest coherent structure tied to a single galaxy. It has expanded our very definition of what a galaxy is, not just a city of stars, but an engine that can project its influence across distances that truly beggar the imagination. And if this kind of deep dive into the mind-bending scales of the cosmos fascinates you, if you love having your perspective shifted by the sheer wonder of what's out there, then consider subscribing. We explore these kinds of questions every week, and by joining us, you won't miss the next journey into the incredible frontiers of science. The bigger picture: a universe of giants. While the epic clash between IC 1101 and Alcyoneus grabs our imagination, it's important to remember they aren't alone in the Cosmic Hall of Fame. The universe is filled with a spectacular variety of massive galaxies, and by studying them, we learn that there are many ways to become a titan. For instance, not all giants are formless blobs like IC 1101. There are also colossal spiral galaxies. The current record holder for the largest known spiral is a galaxy named UGC 2885, nicknamed Rubin's Galaxy. Located about 232 million light-years away, its magnificent spiral disk spans about 832,000 light-years, making it roughly 8 times the diameter of the Milky Way. Unlike IC 1101, UGC 2885 is a relatively isolated, gentle giant. It hasn't grown through violent mergers. Instead, it seems to have been slowly sipping hydrogen gas from the space around it for billions of years, fueling its slow but steady growth. It's a beautiful counterpoint to the cannibalistic nature of cluster giants. Then there are other famous giants like M87, the supergiant elliptical at the heart of the Virgo cluster. While its stellar disk, at about 120,000 light-years across, doesn't rival IC 1101, it's famous for its spectacular, highly visible jet of plasma shooting from its core. It was M87's black hole that was the subject of the first ever direct image of a black hole's shadow. The M87 jet is a powerful reminder that the processes creating the lobes of Alcyoneus are happening all over the universe, just on different scales. The very existence of such massive galaxies so early in the universe is a major puzzle for astronomers. Our standard models say galaxies should grow slowly, with small ones merging over billions of years. But recent discoveries are challenging this idea. Telescopes have allowed astronomers to peer back to the dawn of cosmic time. They have found shockingly massive galaxies that existed when the universe was just a fraction of its current age. For example, a protocluster named SPT 234956, seen as it was just 1.4 billion years after the Big Bang, shows more than 30 gas-rich galaxies all in the process of a massive, chaotic merger. This suggests that some giant galaxies might not form slowly, but in rapid, spectacular pileups. These early giants are forming stars at rates thousands of times that of the Milky Way, hinting at a much more violent and accelerated path to bigness. New technologies are giving us new ways to study the lives of these giants. By analyzing the chemical makeup of stars in different parts of a galaxy, astronomers can create chemical maps that trace a galaxy's history of mergers over billions of years. This cosmic archaeology allows us to piece together how a galaxy like IC 1101 assembled itself from its many smaller victims. The story of the largest galaxies is a moving target. What we know today will almost certainly be revised by the discoveries of tomorrow. The champions, IC 1101 and Alcyoneus, are simply the most extreme examples we've found so far. They represent two main paths to becoming a giant: the slow accumulation of stars, and the explosive influence of a black hole. But the universe is vast and full of surprises. Somewhere out there, an even larger giant may be waiting to be found, one that will once again force us to redraw our maps of the cosmos. A universe of wonder. So, what is the largest galaxy ever observed? As we've seen, the answer isn't a single name, but a story. A story about how we measure the universe and, in turn, how the universe challenges our definitions. If by largest you mean the greatest city of stars, the most massive single collection of suns bound by gravity, then the crown likely still belongs to the old king, IC 1101. Its vast halo of 100 trillion stars is a monument to billions of years of cosmic conquest. It represents bigness in its most solid, material form. But if by largest you mean the grandest structure, the single galactic entity with the farthest reach, then the title has passed to Alcyoneus. Its almost unbelievable 16.3 million light-year span is not made of stars, but of the ghostly plasma plumes from its central black hole. It is a giant of influence, a testament to the power of these engines to project their presence across scales that dwarf even the biggest collections of stars. Ultimately, this isn't about declaring a single winner. It's about appreciating the breathtaking scale and diversity of the cosmos. The universe has more than one way to be gigantic. The rivalry between the stellar giant and the radio behemoth teaches us that what we see isn't always what we get. The most spectacular structures can be hidden from our eyes, waiting for new ways of looking at the sky to reveal them. This journey from IC 1101 to Alcyoneus is a perfect snapshot of how science works. A long-held belief is suddenly challenged by a new discovery, made with new technology. A simple question, "What's the biggest?" leads to a deeper, more complex understanding. It forces us to refine our very concepts. And the story is far from over. Somewhere in the unobserved darkness, an even larger structure almost certainly lurks. Perhaps it's an even bigger stellar halo, or radiolobes that dwarf even those of Alcyoneus. Or maybe it will be something entirely new, a form of galactic bigness we haven't even imagined yet. That's the real wonder of it all. The universe isn't a static museum of facts. It is a living, evolving mystery that we are only just beginning to unravel. The quest to find the biggest, the fastest, the oldest, is our way of being part of that unfolding story. Every new discovery, every broken record, isn't an endpoint, but a new signpost, pointing us toward an even deeper and more profound understanding of our place in the cosmos. The hunt is what matters, because it ensures that we will always keep looking up, and always keep wondering. Part 2: What a galaxy actually is. Before we can decide what the largest galaxy ever observed might be, we have to slow down and ask a quieter question. What is a galaxy, really? It sounds almost too simple to ask. Most of us have seen the photographs. A glowing spiral. A soft oval of ancient light. A strange patch of stars that looks smeared across the dark. We call all of them galaxies, and because the word feels familiar, it is easy to think we already understand it. But a galaxy is one of those things in astronomy that becomes stranger the longer you look at it. From far away, a galaxy can seem like an object, almost like a jewel hanging in space. But a galaxy is not a single thing in the way a planet is a thing, or even in the way a star is a thing. A galaxy is more like a vast community, or a long-lived ecosystem, or a kingdom built by gravity over billions of years. It contains stars, yes, but also gas, dust, planets, dead stars, black holes, magnetic fields, and a great invisible framework of dark matter holding the whole structure together. NASA and ESA both describe galaxies as enormous systems of stars, gas, dust, and dark matter bound by gravity, and note that the largest can contain trillions of stars. That word, gravity, is the quiet key to everything. If you took all the stars in some patch of space and they were not bound together by gravity, they would not be a galaxy. They would just be stars passing through the same darkness. A galaxy exists because gravity has spent immense stretches of time gathering matter, shaping it, holding it, and in some cases feeding it into even denser structures near the center. A galaxy is what happens when the universe gives matter enough time to organize itself into something huge, beautiful, and durable. And already, there is something calming about that idea. The galaxy is not rushed. It does not appear in a flash. It is assembled patiently. One generation of stars lives and dies, and the galaxy remains. Clouds of gas drift for millions of years, and the galaxy remains. Even collisions between galaxies, which sound violent to us, unfold over hundreds of millions of years. In cosmic terms, a galaxy is less like an explosion and more like a continent slowly taking shape. NASA and ESA describe galaxy interactions and mergers as key parts of galaxy evolution, and note that individual mergers can take hundreds of millions of years to complete. The easiest part of a galaxy to notice is the starlight. That is what our eyes, and early telescopes, were built to see. The stars make the visible body of a galaxy. When people picture the Milky Way, or Andromeda, or the great glowing spirals in Hubble images, they are usually thinking of the stars first. And that makes sense. Stars are the bright neighborhoods. They are the candles in the window. They are what turn a dark structure into something visible across impossible distances. But stars are only the beginning. Between the stars lies gas and dust, and this material matters more than people often realize. Gas is the raw fuel for future stars. Dust, though it sounds almost trivial, helps cool that gas and allows it to gather into denser clouds. In giant molecular clouds, gravity can slowly pull material inward until new stars are born. That means a galaxy is not just a collection of stars that already exist. It is also a place where stars are still being made, where the next generation is quietly forming in cold, dark nurseries hidden from ordinary sight. NASA describes stars as forming in large molecular clouds of gas and dust, sometimes spanning hundreds of light years. So when you look at a galaxy, you are not looking at a finished object. You are looking at an ongoing process. Some parts are bright with youth. Other parts are older, redder, calmer. Some regions are rich with gas and still active. Others have already used most of their fuel and settled into a slower old age. In that sense, galaxies are a little like forests. Some areas are thick with new growth. Others are ancient and quiet. Some have recently been disturbed. Others have been left alone for so long that their shape has become smooth and settled. And then there is the part we cannot see at all. Modern astronomy tells us that most of the mass in a galaxy is not in the stars, and not in the gas, and not in the dust. It is in dark matter, a mysterious form of matter that does not shine, does not absorb light in the ordinary way, and yet reveals itself through gravity. NASA notes that dark matter makes up most of the mass in galaxies and galaxy clusters and helps shape the cosmos on large scales. In simple terms, dark matter acts like the deep, invisible skeleton of a galaxy. The visible galaxy is what grows inside that framework. This is one of the strangest and most beautiful facts in astronomy. The part of the galaxy that looks most impressive to us, the starlight, is not the whole story and may not even be the main story. The shining spiral arms and soft golden halos are only the visible expression of something much larger and deeper. In a way, galaxies are built from an invisible architecture, and the stars are just where that hidden design catches the light. That matters a great deal when we start talking about size. Because if a galaxy has a visible body of stars, and a much larger halo of dark matter, then what exactly are we measuring when we say a galaxy is big? Are we measuring the bright part? The faint outskirts? The invisible gravitational reach? The answer changes depending on which layer of the galaxy we care about. And that is one reason the question of the largest galaxy becomes far more slippery than it first appears. But before we get there, it helps to understand the main shapes galaxies take. Astronomers usually place galaxies into three broad families: spiral, elliptical, and irregular. Spiral galaxies are the ones people tend to love at first sight. They have disks, central bulges, and graceful arms winding outward like cosmic storms frozen in light. Our own Milky Way is a spiral galaxy. NASA notes that spiral galaxies are rich in gas and dust and are often still forming stars, which is one reason they can look bright and blue in places. Elliptical galaxies, by contrast, tend to have smoother, rounder, or more stretched shapes and often contain older stars. Irregular galaxies are the odd ones, the disrupted ones, the galaxies that do not settle neatly into either of the first two categories. That classification sounds neat on paper, but in reality galaxies live messy lives. A spiral galaxy can collide with another galaxy and lose its clean shape. A galaxy that once had graceful arms can be stripped of gas, leaving behind a smoother, quieter form. A cluster giant can grow by swallowing smaller neighbors until it becomes a huge elliptical city of old stars. A small irregular galaxy may simply be what remains after many gravitational disturbances. In other words, a galaxy's shape is not just a label. It is a memory. It tells a story about what that galaxy has been through. And that story can be long. Long enough that an entire civilization on Earth could rise, vanish, and be forgotten while two galaxies are still only halfway through a merger. That is worth lingering on for a moment. We tend to think of the universe as dramatic, full of collisions and eruptions. And it is. But it is also patient beyond anything human life can easily absorb. Even a violent, galactic event often unfolds so slowly that, from one human generation to the next, it would appear almost motionless. A galaxy can be changing all the time and still seem eternal. At the center of many large galaxies lies something even stranger, a supermassive black hole. NASA notes that most large galaxies have one at their centers, and some are billions of times more massive than the Sun. Most of the time, these black holes are not roaming monsters swallowing everything nearby, as movies often suggest. Much of the time they are relatively quiet. But under the right conditions, if enough gas falls inward, the region around the black hole can become intensely bright and active. In some galaxies, that central engine can even launch particles outward at nearly the speed of light. This is where our picture of a galaxy starts to get even more interesting, because many people still imagine a galaxy as mostly a star system on a large scale, a larger version of the Milky Way band you see in the sky. But the truth is that a galaxy can be far more than a place where stars live. It can also be a machine. Not a machine built from metal, but a natural engine built from gravity, magnetism, plasma, and time. In some cases, the central black hole does not just sit at the center of the galaxy. It reshapes the space far beyond the visible stars through jets and radio-emitting lobes that stretch outward for astonishing distances. The discovery paper on Alcyoneus in 2022 described it as a radio galaxy with a projected proper length of about 4.99 megaparsecs, and by 2024 researchers reported Porphyrion, a giant black hole jet system spanning roughly 7 megaparsecs. Those structures are much larger than the visible host galaxies that launched them. And this is where the calm little question, what is a galaxy, quietly opens into something much bigger. Is a galaxy only the bright central body of stars? Or should we also count the enormous structures generated by the black hole at its heart? When a galaxy sends jets far into intergalactic space, and those jets remain physically tied to the galaxy's central engine, are they part of the galaxy's true extent, or are they something else entirely? You can feel the question shifting under your feet. Because a moment ago, the word galaxy may have sounded simple. A spiral, a cloud of stars, a bright island in the dark. But now the galaxy is becoming harder to contain. It has visible parts and invisible parts. It has an inside life and an outside influence. It has a present form and a history written into its shape. It may be calm for billions of years, then suddenly active enough to hurl matter across millions of light years. A galaxy is not just a place. It is a deep time structure. There is also something a little humbling in realizing that our own home galaxy, the Milky Way, is only one example among countless kinds. It feels immense to us because it contains our sun, our night sky, our local neighborhood of stars. But in the wider universe, galaxies come in enormous variety. Some are small dwarfs with only modest populations of stars. Some are giant ellipticals full of ancient light. Some are misshapen after close encounters. Some live quietly. Some blaze with black hole activity. Some are rich in the cold gas needed to make future stars. Some have already spent most of that fuel and entered a slower age. So when we say galaxy, we are not naming one kind of object. We are naming a family of cosmic lives. That is why the largest galaxy question matters. Not because it gives us a neat record book answer, but because it forces us to define what we mean by a galaxy in the first place. If stars alone define it, one answer may win. If a galaxy's full physical influence counts, another answer may take the crown. And if we include the faint outskirts, the hidden halo, or the vast radio structures blown into space by the core, then the entire conversation changes. Before we go further, let me leave a quiet invitation here. If this calm journey through the universe is helping you settle in for the night, a gentle like or subscribe is always appreciated. And if there is a galaxy you've always found especially beautiful, whether it is Andromeda, the Whirlpool Galaxy, or something more obscure, you can leave its name in the comments. I always like seeing which corners of the cosmos stay with people. For now, though, the important thing is this. A galaxy is not just a picture in a telescope. It is not just a bright wheel of stars. It is a layered structure held together by gravity, built inside an invisible dark matter framework, fed by gas and dust, shaped by mergers, and in many cases anchored by a supermassive black hole. Some galaxies are nurseries. Some are graveyards of older stars. Some are graceful. Some are broken. Some are quiet. Some project their influence astonishingly far beyond what visible light alone would ever suggest. And once you understand that, the question of the largest galaxy becomes much more interesting than it first seemed. Because the winner depends on what part of the galaxy you believe is the real galaxy. Is it the starlight? The faint halo? The invisible mass? The reach of the black hole? The answer is not obvious, and that uncertainty is where the real wonder begins. So the next time you see a galaxy in an image, try not to think of it as a single object with a clean edge. Think of it instead as a slow, gravitational civilization. A place where stars are born, where ancient suns drift in vast numbers, where invisible matter does most of the heavy lifting, and where a hidden engine at the center may, under the right conditions, throw its presence across the dark for millions of light years. That is what a galaxy actually is. Not a dot, not a decoration, but a deep and living structure in the universe, far stranger than the word itself first suggests. And now that we know what a galaxy is, we are finally ready to ask the harder question. When astronomers say one galaxy is larger than another, what exactly are they measuring? Part 3. Why largest galaxy is harder than it sounds? If someone quietly asked you what the largest mountain on Earth is, the answer would come quickly. Everest. If they asked for the largest ocean, that would feel simple too. The Pacific. We like questions like that because they seem clean. They promise a winner. One name, one crown, one final answer. But the universe is not always so cooperative. When we ask what the largest galaxy ever observed is, it sounds like the same kind of question. We imagine that astronomers must already have a neat cosmic ruler, and somewhere in a catalog there must be one object sitting comfortably at the top of the list. Biggest. End of story. And yet, the deeper you go, the less tidy that answer becomes. Because a galaxy is not a marble. It does not come with a clean edge. It does not sit in space like a solid object with a bright outline and a simple diameter. A galaxy fades. It stretches. It hides part of itself. It influences regions far beyond the starlight we first notice. And depending on what exactly you choose to measure, the answer to the question can change. That is the quiet trap inside this whole mystery. At first, it sounds like we are trying to identify the biggest galaxy. But in reality, we are trying to decide what a galaxy even counts as when it begins to blur into the larger universe around it. And this is where the story becomes far more interesting. Because once you stop looking for a quick answer and start asking how astronomers actually measure these things, you realize that largest is not one question at all. It is several questions wearing the same mask. One way to measure a galaxy is by the part that glows with stars. This is the most intuitive method, and it is also the one that feels most natural to people who are new to astronomy. You point a telescope at a galaxy, you see the light from its stars, and you try to estimate how far that visible structure extends. NASA describes galaxies as enormous systems of stars, gas, dust, and dark matter bound together by gravity, with the largest containing trillions of stars. That visible starlight is the first thing we notice, and for a long time it was the main way people thought about galactic size. And on the surface, that seems reasonable. After all, if you want to know how large a city is, you might start with the buildings. If you want to know how large a forest is, you might begin with the trees. So if you want to know how large a galaxy is, why not start with the stars? But even that first method turns slippery the moment you look closely. Because a galaxy's starlight does not simply stop. It gets fainter and fainter, slowly fading into darkness. Near the center, the stars may be crowded and bright. Farther out, they thin into dim halos so faint that it becomes difficult to say where the galaxy truly ends and where empty space begins. In a sense, the edge of a galaxy is often not a sharp border, but a judgment call. That means two astronomers, using different instruments or different brightness thresholds, might not draw exactly the same outer line. One might focus on the brighter main body. Another might include the faint stellar halo. And if the halo is huge, that difference matters a lot. This is one reason older answers about the largest galaxy often pointed toward giant elliptical systems like IC 1101. In visible light, especially if you include its immense faint halo, IC 1101 became famous as an almost absurdly large stellar system. It was the king of the visible giants, the kind of galaxy that seemed to settle the matter for decades. But what made it seem largest depended heavily on the fact that astronomers were measuring the luminous reach of its stars, especially its extended outer halo, not every other possible kind of structure attached to it. And this leads to the next complication. Stars are not the only important part of a galaxy. A galaxy also contains gas and dust, and these do not always line up neatly with the visible stellar edge. Spiral galaxies, for example, can be rich in gas and dust far out into their disks, beyond the regions that dominate a photograph. NASA notes that spiral galaxies are rich in the gas and dust needed to form new stars, and that spiral systems are surrounded by halos containing old stars, star clusters, and dark matter. So the visible galaxy is already only part of the full system. If you were patient enough, and your instruments were sensitive enough, you might discover that the gas extends beyond the brighter starlight. In some galaxies, especially disturbed ones or galaxies that have interacted with neighbors, material can be pulled outward into long tidal streams, faint arcs, and ghostly structures. These may not look dramatic at first glance, but they are still part of the galaxy's story. And stories matter in astronomy. Because galaxies are not static decorations. They are things that live through mergers, close encounters, eruptions from their centers, and long periods of quiet aging. ESA's Hubble team notes that galaxy mergers are slow, stately events that can take hundreds of millions of years to complete. So when we observe a galaxy, we may not be seeing a tidy object in equilibrium. We may be catching it in the middle of a very long transformation. Now imagine trying to measure something while it is still being reshaped by gravity. A tidal stream flung outward during a merger may remain visible for a long time. A shell of stars might mark the remains of a galaxy that was swallowed in the past. Should those structures count toward the size of the present galaxy? Some astronomers would say yes, because they are gravitationally connected remnants of its growth. Others may treat them more cautiously, especially if the structure is diffuse or temporary. And if that sounds like a technical quibble, it really is not. It goes straight to the heart of the question. Because the answer depends on whether you think a galaxy should be measured by its bright central body, by everything gravitationally associated with it, or by every structure physically generated by it. Those are not the same thing. And the deeper complication is still ahead. Because there is one part of a galaxy that is even harder to see than its faint stellar halo, and that is dark matter. This is where the whole idea of largest begins to drift into almost philosophical territory. Dark matter does not shine. It does not give us a pretty image. It does not trace elegant spiral arms or soft golden ellipses across the sky. But astronomers infer that it provides most of the mass in galaxies, creating vast invisible halos that extend far beyond the visible stars. NASA describes dark matter as making up most of the mass in galaxies and galaxy clusters, shaping the structure of the cosmos through its gravity. So now we have to ask a very uncomfortable question. If most of a galaxy's mass is in an invisible halo much larger than the part we can see, then what is the true size of the galaxy? Is it the diameter of the starlight? Or is it the full reach of the dark matter halo? If we choose the second answer, then the winner in any largest galaxy contest might be very different from the one most people expect. But the problem is that dark matter halos are not easy to measure precisely. They are inferred through gravitational effects, not seen directly. So the answer becomes not just more complicated, but less visually satisfying. There is no single crisp photograph of a dark matter halo saying, "Here it is, this is the edge." And yet, even this is not the end of the story. Because modern astronomy has shown us that some galaxies do something even stranger. They project their influence into space far beyond their stars through gigantic jets and lobes powered by their central black holes. This is the point where the idea of a galaxy starts to feel almost too large for the word itself. At the center of many massive galaxies lies a supermassive black hole. Most of the time, it may be quiet. But if enough material falls inward, the region around the black hole can become violently active, launching enormous jets of radiation and particles into intergalactic space. Over immense stretches of time, those jets can inflate giant radio lobes, structures that are not bright in visible light but glow in radio wavelengths. In 2022, astronomers reported Alcyoneus, a giant radio galaxy whose projected proper length was measured at about 4.99 megaparsecs, making it the largest known structure of galactic origin at the time. What made Alcyoneus so important was not the ordinary-looking host galaxy itself, but the astonishing size of its radio-emitting lobes. And then, as if the universe wanted to make the question even messier, a 2024 report described an even larger black hole jet structure, about 7 megaparsecs, or roughly 23 million light-years, extending from a distant active galaxy. In other words, the largest black hole-driven structure we currently know is even bigger than Alcyoneus, depending on how exactly one defines the system. Now pause there for a moment, because this is where the ordinary language begins to wobble. If a galaxy launches jets so vast they stretch for tens of millions of light-years, are those jets part of the galaxy? If you answer yes, then the largest galaxy might not be the one with the most stars or the widest visible halo. It might be the one whose black hole has managed to project its influence farthest into the cosmic dark. If you answer no, and you insist that only the star-filled host counts as the galaxy, then you may keep the crown on a visible giant like IC 1101 or another enormous stellar system. This is why the question does not behave. It is not just asking for a number. It is asking for a definition. And definitions in science are powerful things. They decide what gets counted. They decide what gets compared. They decide whether a discovery overturns the old answer or simply creates a new category. This is also why headlines can be confusing. One article may say the largest galaxy ever found is a giant elliptical full of stars. Another may point to Alcyoneus. Another may focus on the even larger black hole jet system reported in 2024. Each can sound confident, and each may be using a different measuring rule. None of them are necessarily being dishonest. They may just be measuring different aspects of galactic reality. And perhaps that is the most important thing to understand. The universe does not always sort itself into the categories our language prefers. We want one champion because it feels satisfying. But nature often gives us several overlapping truths instead. The largest stellar body is one kind of answer. The largest dark matter-dominated system might be another. The largest radio structure physically launched by a galaxy's central engine may be another still. So the problem is not that astronomers are confused. The problem is that galaxies are more complicated than the question makes them sound. A galaxy can be a city of stars. It can be a halo of invisible matter. It can be a machine powered by a black hole. It can be all of those things at once. And depending on which face of the galaxy you choose to look at, you may see a different giant staring back at you. There is something strangely beautiful in that, because it reminds us that science is not just about collecting answers. It is also about learning which questions are secretly larger than they first appear. What is the biggest galaxy? Sounds like a simple childlike curiosity, and in a way it is. But it opens onto some of the deepest parts of astronomy. What galaxies are made of, how they grow, how black holes reshape them, and how the invisible parts of the universe matter just as much as the bright parts. In other words, this question is not really about winning. It is about perspective. If you are measuring by visible stars, you get one universe. If you are measuring by radio lobes and black hole activity, you get another. If you are thinking in terms of dark matter halos and total gravitational reach, the picture becomes larger still. The galaxy does not change, but our way of looking at it does. And that may be the quiet lesson hidden inside all this. Very often, in astronomy and in life, the answer depends on where you decide the edges are. If this slow journey through the cosmos is helping you settle in, and you'd like more of these quiet explorations, you can gently subscribe, leave a like, or share a thought in the comments. I always enjoy seeing which parts of these long questions stay with people the most. For now, though, let's bring this piece together. The reason the largest galaxy question is harder than it sounds is simple in principle, even if the details are vast. A galaxy has no perfectly neat edge. Its stars fade outward. Its gas may stretch beyond its bright body. Its dark matter halo extends farther still. Its black hole may launch structures that reach into intergalactic space. Mergers can leave behind faint debris, and different telescopes reveal different versions of the same object. Galaxies are not cleanly bounded islands. They are layered, evolving systems. So when astronomers argue over the largest, they are not only comparing objects. They are deciding what counts as the object. And once you understand that, the mystery becomes far more satisfying. Because now the question is no longer, why can't they give me one answer? Now the question becomes, what exactly do I mean when I say galaxy? That is the question we needed to ask before moving on. Because in the next part, once we accept that size depends on the method, we can finally slow down and look at the tools themselves. How do astronomers measure something this enormous at all? How do you take a structure billions of light years away, with no solid edge, no ruler, and no obvious boundary, and turn it into a number? That is where the real cosmic measuring tape begins. Part 4. How astronomers measure something so far away. By now, the question has become more slippery than it first appeared. We are no longer simply asking which galaxy is the biggest. We are asking what part of a galaxy counts, where its edges truly are, and why different answers can all sound convincing at the same time. And once you reach that point, a second question rises quietly behind the first one. How do astronomers measure something so far away at all? Because it is one thing to say a galaxy is large. It is another thing entirely to turn that feeling into a number. You cannot stretch a tape measure across the void. You cannot fly out there, circle the galaxy, and report back with a neat diameter. All you really receive on Earth is light, or in some cases radio waves, infrared radiation, or other signals that have traveled for millions or billions of years to reach us. That is all. A whisper across the dark. And somehow, from that whisper, astronomers have to figure out not only what the object is, but how far away it sits, how wide it appears in the sky, and how large that apparent width becomes when translated into physical space. That sounds almost impossible at first. But astronomy has always been, in part, the art of learning how to measure things you can never touch. And in a quiet way, that is one of the most beautiful parts of it. Because before astronomers can tell you whether a galaxy is 100,000 light-years wide or several million light-years across, they have to solve two separate puzzles. First, they have to know how far away the galaxy is. And second, they have to know how much of the sky that galaxy covers from our point of view. Only then can the real estimate begin. The easiest part to imagine is the second one. When astronomers look at a galaxy through a telescope, they can measure its apparent size on the sky. Not its true physical size yet, just the angle it seems to occupy. NASA and ESA both note in their image guides that an object's actual size depends on its distance, while its appearance on the sky is described in angular measurements like arcminutes and arcseconds. 1 arcsecond is just 1/3600th of a degree, an almost absurdly tiny slice of the sky. That means a galaxy can look tiny and still be enormous. You have probably felt this in daily life without thinking about it. A mountain far away can fit behind your thumb. The moon looks modest in the sky, even though it is thousands of kilometers wide. Apparent size and true size are not the same thing. They only become connected once you know the distance. And distance is where astronomy becomes both patient and clever. For the nearest stars, astronomers can use a method called parallax. As Earth moves around the Sun, nearby stars appear to shift slightly against the background of more distant stars. That tiny shift gives away their distance. But galaxies, except for the very nearest, are much too far away for ordinary parallax to work in the simple way it does for nearby stars. So astronomers need other methods. They build what is often called the cosmic distance ladder, a chain of techniques where each step helps calibrate the next. NASA and ESA describe Cepheid variable stars as one of the crucial rungs in this ladder, because their predictable brightness changes let astronomers estimate distances to nearby galaxies with remarkable power. This is one of those moments where the universe feels surprisingly generous. Hidden inside certain galaxies are stars that pulse. They brighten and dim in a regular pattern. And astronomers discovered that for Cepheid variable stars, the timing of that pulse is linked to the star's true brightness. If you know how bright the star really is, and then compare that to how bright it appears from Earth, you can estimate how far away it must be. A distant candle looks fainter than a nearby candle, even if both are equally bright. The same logic works across the cosmos. It is a wonderfully human kind of reasoning. Quiet, indirect, and careful. You do not ask the universe for the answer directly. You infer it. And once Cepheids helped astronomers anchor the distances to nearer galaxies, those measurements could then be used to calibrate even brighter markers, like Type Ia supernovae, which can be seen much farther away. NASA explains that Type Ia supernovae are useful as standard candles, because they reach a similar intrinsic brightness, allowing astronomers to estimate their distances from how bright they appear to us. So already, by layering methods on top of one another, astronomers begin to reach outward. Nearby galaxies can sometimes be measured using individual stars like Cepheids. Farther galaxies may require brighter mileposts, like supernovae. And for galaxies far beyond that, where even those tools become difficult, astronomers rely increasingly on the redshift of light. This is where the story widens from simple geometry into cosmology itself. Because the universe is expanding, and as it expands, the light from distant galaxies is stretched to longer, redder wavelengths. The more distant the galaxy, in general, the greater its redshift. Noir Lab describes redshift as a key tool for mapping the three-dimensional universe, since measuring galaxy redshifts lets astronomers infer how far away those galaxies are across immense cosmic scales. This means that when astronomers study a very distant galaxy, they are often using more than a photograph. They are reading the light almost like a fingerprint. A spectrum tells them how much the light has been shifted. That shift gives them a handle on distance. And once they have distance, the galaxy's apparent width on the sky can finally be converted into a physical size. In the simplest form, it sounds almost elegant. Angular size plus distance gives true size. But in practice, nothing is ever that gentle. Because galaxies do not arrive with one clean outline. They arrive as patterns of light with bright centers, faint outskirts, hidden halos, and sometimes strange asymmetries caused by mergers or jets or tidal interactions. So even after the distance is known, astronomers still have to decide what exactly they are measuring. Imagine you are looking at a city from far above at night. Do you measure the bright downtown core? The dimmer neighborhoods? The roads stretching outward? The haze of light beyond the suburbs? Depending on where you draw the border, the city changes in size. The same is true for galaxies. A galaxy seen in visible light might appear to have one diameter. But when observed in radio wavelengths, it might reveal enormous structures beyond the stars. In infrared, dust-obscured regions may come into view. In ultraviolet, young hot stars stand out more strongly. In X-rays, energetic regions near a black hole may dominate. There is no single galaxy picture that tells the whole truth. Different wavelengths show different layers of the same cosmic life. That matters a great deal for the largest galaxy question. Because when astronomers measure something like a giant elliptical galaxy, they may be focusing on its stellar envelope, including the very faint outer light of its halo. But when they measure a giant radio galaxy, they may be including enormous radio lobes blown out by jets from the central black hole. The method changes the answer because the instrument changes what counts as visible. And that is not cheating. That is reality. The universe is multi-layered. We only ever see part of it at a time. This is one reason astronomy depends so deeply on combining different telescopes and different wavelengths. Hubble, Webb, radio arrays, X-ray observatories, all of them are looking at the same universe from different angles, each one revealing a different truth that the others might miss. For very large galaxies, especially the strange and extraordinary ones, this becomes essential. A galaxy like IC 1101 became famous largely because of its vast visible extent, especially once astronomers considered its enormous faint stellar halo. A galaxy like Alcyoneus became astonishing because radio observations revealed lobes reaching far beyond what ordinary visible light images would suggest. The galaxy did not suddenly become bigger in 2022. What changed was our ability to see the hidden part of its structure. And perhaps that is worth sitting with for a moment. Sometimes, in astronomy, an object grows not because it changed, but because our eyesight did. The telescope becomes a kind of humility machine. It reminds us that the universe was always larger than our first impression of it. There is another quiet difficulty here too. The farther away a galaxy is, the farther back in time we are seeing it. Light does not arrive instantly. It takes time to travel. So a galaxy 1 billion light-years away is being seen as it was roughly 1 billion years ago. In other words, astronomers are never seeing distant galaxies exactly as they are now, in some universal sense. They are seeing old light, a message from the past. This matters because galaxies evolve. A distant giant may still be in the process of changing when the light we see leaves it. A radio structure may be expanding. A merger may be underway. The size we assign is always tied to that observed moment in cosmic history. We are not measuring a timeless object. We are measuring one frame in a very long movie. And yet, even with that limitation, astronomers have become astonishingly good at this work. They map angular size. They calculate distance using the cosmic distance ladder, redshift, and other methods. They observe in multiple wavelengths. They model faint outer structures. They compare brightness profiles. They decide on thresholds, boundaries, and definitions. Then, very carefully, they turn all that into an estimate. Not certainty, usually, but a disciplined estimate. That distinction matters. Because one of the most comforting myths about science is that it always produces perfect numbers. But in astronomy, the reality is calmer and more honest. There are always uncertainties. Distances can be revised. Edges can be redefined. New telescopes can reveal fainter outer regions. Better radio data can uncover larger lobes. Improved processing can pull hidden structure from noise that older instruments missed. That means the answer to, how big is this galaxy, is often something like this. Here is the best current estimate, based on these observations, in these wavelengths, using these definitions. And that is not weakness. It is exactly what careful science looks like. For sleep, and for life really, there is something softening about that. The universe does not always yield a perfect line around itself. Sometimes knowledge comes as a series of increasingly better approximations, each one gentler and truer than the last. If this kind of quiet exploration helps you settle in, a soft like or subscribe is always appreciated. And if you ever saw one of those deep space images and wondered how anyone could possibly turn that into a number, now you know a little of the patient craft behind it. You can also leave a comment about which part feels most mind-bending to you, the distance, the old light, or the fact that a galaxy's size depends on the wavelength you use to look at it. And there is one more thing astronomers have to do before they can compare giants fairly. They have to make sure they are comparing like with like. If one galaxy's size was measured in visible light down to a very faint brightness threshold, but another galaxy's size was measured only from its brighter central regions, then the comparison is uneven. If one radio galaxy includes the full span of both lobes, but another estimate focuses only on the host galaxy itself, then again the comparison is uneven. The measurement is only as meaningful as the definition behind it. This is why the largest galaxy debate often sounds less like a single race and more like several overlapping competitions. Largest stellar extent, largest visible halo, largest radio structure, largest dark matter-dominated system, if such things could be compared cleanly. Each category tells a different story about what galaxies are capable of becoming, and perhaps that is the deepest answer hiding here. Measuring something so far away is not only about technology, it is also about interpretation. The telescope gives you light, the math gives you distance, but then judgment enters quietly. What do we count? Where do we draw the edge? Which wavelength tells the most meaningful version of the galaxy? Those choices shape the universe we think we are seeing. So when astronomers say a galaxy is, for example, hundreds of thousands of light-years across, or millions of light-years from end to end, that number is never just a simple fact plucked from the dark. It is the result of an elaborate chain of reasoning. A tiny angle in the sky, a distance estimated from stellar candles or redshift, a decision about what structures belong to the galaxy, a translation from appearance into reality. That is how the cosmic measuring tape works. It is not laid out in the void. It is built in the mind, from light, geometry, patience, and time. And once you understand that, the size of a galaxy becomes even more astonishing. Not just because the number is large, but because human beings, on one small planet, managed to learn how to uncover it at all. We sit here in the dark, surrounded by our own tiny concerns, and yet we have taught ourselves how to measure systems so far away that their light began its journey before many forms of life on Earth even existed. There is something quietly beautiful in that. A galaxy whispers. And eventually, if we listen carefully enough, it gives us its scale. Which brings us naturally to the next part of the journey. Now that we know how astronomers actually estimate these immense distances and sizes, we are finally ready to meet the giant that changed the whole conversation. Because once the measuring methods are in place, we can stop speaking in abstractions and start looking at the contender itself. The one that made astronomers rethink what the phrase, largest galaxy, might really mean. Part 5, Meet Alcyoneus, the giant. For a very long time, the story felt settled. If you asked about the largest galaxy ever observed, the answer seemed to belong to the old giants, the massive cities of stars whose visible bodies stretched so far across space that they already felt almost unreasonable. It was the kind of answer that gave people comfort. One champion, one cosmic heavyweight, one clear record to place on the shelf. And then, quietly, the universe changed the question. Not because the old giants disappeared. Not because astronomers suddenly forgot how large those stellar kingdoms were. But because in 2022, researchers studying faint radio data found something that did not fit the old picture of galactic size at all. They found Alcyoneus, a giant radio galaxy whose projected length was measured at about 4.99 megaparsecs, or roughly 16.3 million light-years, making it the largest known structure of galactic origin at the time it was reported. And that phrase matters. Not simply a large galaxy, not merely a bright collection of stars, but a structure of galactic origin, something made by a galaxy, and so immense that it forced astronomers to pause and ask whether the word galaxy had been too small all along. There is something almost poetic about that. Because Alcyoneus does not announce itself the way you might expect. It is not the kind of object that, in ordinary visible light, immediately looks like the king of the cosmos. Its host galaxy is not absurdly huge in the familiar way that a giant elliptical can be huge. It does not appear as some impossible island of visible stars filling half the imagination. In fact, one of the most surprising things about Alcyoneus is how ordinary the host can seem compared with the unimaginable scale of what extends from it. The 2022 Discovery paper described the host as a low-excitation radio galaxy and emphasized that its record-setting size was not simply the result of an unusually extreme host galaxy. That is where the mystery begins. It is almost as if the universe hid one of its greatest giants inside an object that did not look, at first glance, like a giant at all. The name itself comes from Greek mythology. Alcyoneus was a giant, the son of the sky god Ouranos, a figure associated with immense strength and a struggle for cosmic dominance. The researchers chose the name with a kind of quiet precision. They had found something giant, yes, but also something that felt mythological in scale, the kind of structure that makes ordinary intuition step back and fall silent. Leiden University's announcement on the discovery made that connection explicit, noting that the structure was named after the giant Alcyoneus from Greek myth. And yet what makes Alcyoneus so extraordinary is not mythology, but physics. At the center of many galaxies lies a supermassive black hole. Most of the time, when people hear those words, they picture something destructive and final, a dark mouth swallowing everything nearby. But black holes can also be engines. If gas falls toward the black hole, that material can heat up, accelerate, and under the right conditions help create jets that shoot out from the galaxy's core at astonishing speeds. Over immense stretches of time, those jets push energy and particles out into intergalactic space, inflating huge radio-emitting lobes. In the case of Alcyoneus, those lobes are the real story. The Discovery paper reports that both the jets and lobes were detected, and together they stretched across nearly 5 megaparsecs in projected length. That is the number that changes everything. 5 megaparsecs. 16.3 million light-years. A distance so large that language almost stops being helpful. You can say the words, of course. You can repeat the number. But the mind does not welcome it easily. It slides off. It does not fit neatly inside human scale. So it helps to slow down and compare. Our Milky Way is about 100,000 light-years across in visible diameter. Alcyoneus, end-to-end, is more than 100 Milky Ways laid in a line. Leiden University's announcement used exactly that kind of comparison, describing the structure as comparable to 100 Milky Ways in a row. And once you picture that, something subtle happens. The Milky Way, which already feels immense to us because it contains our sun, our night sky, our whole local story, suddenly becomes small enough to use as a measuring stick. That is what a true giant does. It makes even the familiar large things feel modest. But perhaps the strangest part is this. If you were hoping for an object that blazes across the sky in visible light, Alcyoneus would disappoint you. Its greatest extent is not something your eyes could appreciate directly, even if they were somehow sharp enough to see across billions of light years. The enormous lobes of Alcyoneus are radio structures, not star-filled visible wanes. They are made of hot plasma and magnetic fields, glowing primarily in radio wavelengths. The discovery depended on LOFAR, the low-frequency radio array used to reveal these faint and extended features. In other words, Alcyoneus had been hidden inside a different kind of light. That, to me, is one of the soft wonders of the whole story. The universe did not suddenly create Alcyoneus in 2022. It had been there the whole time, stretching its ghostly arms through the dark while human beings on Earth went about ordinary life. The structure waited patiently, not for new physics, but for better attention, for instruments sensitive enough to faint radio whispers, for data processing careful enough to let subtle patterns emerge from noise. There is a lesson in that, perhaps. Sometimes the largest thing in the room is invisible until you learn how to look. The team that found Alcyoneus was not, in some dramatic movie-like sense, chasing a giant with a spotlight. The discovery has often been described as partly a stroke of luck, emerging during careful work with radio survey data. Leiden University's announcement says the team found the giant while reprocessing existing images so that weaker radiation stood out more clearly, allowing subtle large-scale features to emerge. That detail matters, because it makes the discovery feel more human. This was not thunder and revelation. It was patience, technique, curiosity. One of those quiet scientific moments where a better method suddenly makes the universe larger than it was the day before. And once Alcyoneus appeared, the obvious question followed almost immediately. How? How could a galaxy produce something so enormous? If the host itself is not outrageously special in the simple visible light sense, then what allowed its lobes to reach such absurd distances? The discovery paper is careful here. It does not present one final answer, but it does explore possibilities connected to the environment around the galaxy and the way giant radio galaxies grow. The researchers were interested in whether the surrounding large-scale cosmic environment, including relatively low-density conditions, might have helped these lobes expand so far. That possibility is deeply important, because it means that bigness may not be only about brute force. It may also be about resistance, or rather the lack of it. Imagine two fires burning with similar energy. One is trapped in a tight stone room. The other opens into a vast empty plain. The second one can spread farther, not necessarily because it is more violent, but because there is less to stop it. Something like that may be true here. If a galaxy's jets are pushing into an environment where the surrounding medium is relatively thin, relatively forgiving, then perhaps those structures can grow to incredible size before fading away. So Alcyoneus may be teaching astronomers something larger than its own record. It may be telling them that the biggest galactic structures are not only a story about the central black hole, they are also a story about the landscape the galaxy lives in. A quiet environment, a supportive geometry, a long runway through the cosmic web. That idea has a certain calm elegance to it. The giant is not merely a bully. The giant is also a product of its surroundings. And perhaps that is why Alcyoneus felt so disruptive to the old conversation. A galaxy like IC 1101 represents one kind of greatness, the greatness of stars, of mass, of accumulated mergers and luminous scale. Alcyoneus represents another kind, a greatness of reach, a greatness of influence, a galaxy that, through its central engine, projects itself far beyond the boundary where starlight would have left the contest. Leiden's 2022 announcement was very clear on this point. It called Alcyoneus the largest structure made by a galaxy known at that time. Not the brightest, not the most star-filled, but the largest structure made by a galaxy. That single distinction reshaped the argument. And that reshaping is exactly why this part of the story matters so much. Because Alcyoneus is not just a contender in a cosmic ranking. It is the turning point where the ranking itself begins to feel inadequate. Before Alcyoneus, many people could imagine the largest galaxy as something like an exaggerated visible system. More stars, more halo, a bigger and bigger island of light. After Alcyoneus, the imagination has to stretch in a different direction. Now the galaxy is not just an island. It is an engine. It is not just what shines. It is also what it sends outward. And once you accept that, the whole universe becomes less tidy and more magnificent. There is also something almost haunting about the scale involved here. Leiden's announcement notes that despite being about 3 billion light-years away, the structure looms as large in the sky as the Moon, which is only possible because it is so physically vast, even though its radio glow is faint. That is a remarkable image to hold in the mind. A ghostly, giant structure, distant beyond intuition, yet on the sky it spans a comparable angle to the Moon because its true length is so extraordinary. That is the kind of fact that can keep you awake for a moment, before it lulls you into a deeper kind of awe, because the Moon feels close, familiar, manageable. But Alcyoneus, at billions of light-years away, wears a similar apparent width only because it is so unreasonably large. This is why astronomy can feel like a dream at times. The numbers are real, and yet they feel invented. They seem to belong more to myth than to matter. And still, there they are, patiently measured from radio waves drifting into our instruments after traveling across the long dark. Of course, the story does not fully end with Alcyoneus. Since then, astronomers have reported an even larger black hole-driven jet system, Porphyrion, spanning roughly 23 million light-years, which was presented in 2024 as an even bigger cosmic jet structure than Alcyoneus. But that does not diminish Alcyoneus's role in this journey. It remains one of the great turning points, because it was the discovery that dramatically exposed how large a galaxy-made structure could be and how incomplete our older intuitions had been. And in a way, that makes Alcyoneus even more important. Not necessarily because it will hold every record forever, but because it changed the way the records are imagined. Some discoveries are famous for being the first mountain climbed, others for being the moment people realized there were mountains in the first place. Alcyoneus belongs to that second category. It widened the frame. It made the old answers feel provisional. It reminded everyone that the universe still had room to surprise us with new dimensions of scale. If this calm kind of cosmic storytelling is helping you ease into the night, a gentle like or subscribe is always welcome. And if you want, you can leave a comment with which kind of giant fascinates you more, the visible giant full of stars, or the hidden giant revealed only in radio light. I always enjoy seeing which kind of universe people feel drawn toward. For now, though, let us stay with Alcyoneus a little longer. Try to picture it, not as a photograph, because no ordinary photograph really captures what matters most here. Picture instead a fairly ordinary-looking host galaxy, far away in the dark. At its center, a supermassive black hole. From that core, over unimaginable time, energy and matter stream outward in opposite directions. The jets move. The lobes swell. Space yields just enough. Millions of years pass. More millions. The structure grows and grows until it reaches a scale that, from end to end, becomes one of the largest galactic origin structures ever detected. And all the while, from Earth, nothing in the night sky announces it in simple starlight. It takes radio eyes to see the giant. That is Alcyoneus. Not merely big, not merely faint, but quietly transformative. It takes the old question, what is the largest galaxy ever observed, and answers it not with a final certainty, but with a richer and stranger possibility. Maybe the biggest galaxy is not the one with the largest visible body of stars. Maybe the true giant is the one whose central engine has pushed its influence farthest into the universe. Maybe the galaxy is larger than the light we first think to measure. And once that thought enters the mind, it changes the mood of the whole search. Now we are no longer hunting for one glowing champion alone. Now we are listening for giants hidden in the dark. That is why meeting Alcyoneus matters. Because once you meet it, the universe becomes harder to simplify again. And that sets the stage perfectly for what comes next. Because it is one thing to hear that Alcyoneus is enormous. It is another to actually feel how enormous it is. And the only way to do that is through comparison. Against the Milky Way. Against the old visible giants. against the scales we thought we already understood. That is when the numbers stop being abstract and start becoming almost unsettling. That is when the giant begins to feel real. Part 6. How large is that compared with the Milky Way? Numbers can be honest, and still fail us. That is one of the quiet frustrations of astronomy. You can say that Alcyoneus stretches for about 16.3 million light-years from end to end, and every word in that sentence can be correct. The number can sit there on the page, precise and well-behaved, and yet the mind still does not know what to do with it. It feels too large to enter the imagination cleanly. It does not settle. It hovers. So this part of the journey is not really about introducing a new fact. It is about making the fact feel real. Because if Alcyoneus is going to mean anything to us at all, it cannot remain just a number. It has to be compared to something we already know. It has to be set beside the Milky Way, our home galaxy, the one scale we carry with us almost instinctively whenever we think about the wider universe. And once we do that, the size of Alcyoneus starts to become less abstract and more unsettling. The Milky Way, according to NASA and ESA, is about 100,000 light-years across in its main disk, and our solar system sits roughly 26,000 light-years from the galactic center. The Sun takes about 250 million years to orbit that center once. These are already enormous numbers by any ordinary standard. The Milky Way is not a modest thing. It is a city of stars so large that light itself needs about 100,000 years to cross its main disk. And that is exactly why the comparison works. Because the Milky Way already feels huge enough to us. It contains our Sun, our planets, our constellations, the soft milky band across the night sky, and the hidden center around which our whole local story slowly turns. If even the Milky Way can be made to feel small, then something genuinely extraordinary must be happening. Now place Alcyoneus beside it. The 2022 Discovery paper describes Alcyoneus as a giant radio galaxy with a projected proper length of about 4.99 megaparsecs, or roughly 16.3 million light-years. Leiden University's announcement put it another way: it is about 100 Milky Ways in a row. If we compare that figure directly to the Milky Way's roughly 100,000 light-year diameter, the end-to-end size of Alcyoneus comes out to about 160 Milky Ways laid side by side, depending on which Milky Way boundary you use for the comparison. That is the first moment where the mind begins to blink. 100 Milky Ways, or more. Not a little larger. Not twice as wide. Not even 10 times the size of our home galaxy. But more like an entire procession of Milky Ways, one after another, stretched across the dark until the number itself starts to feel dreamlike. And yet that comparison still does not go quite far enough, because rows of galaxies are hard to picture. So let us make it more intimate. Imagine standing inside the Milky Way, somewhere near the position of our Sun, and trying to understand what it means for our home galaxy to be 100,000 light-years wide. Even that is almost too much. The light arriving from some distant stars in our galaxy tonight began its journey long before human civilization existed. If a beam of light left one edge of the Milky Way when early humans were just beginning to spread widely across Earth, it still would not have crossed the full disk by now. That is how large home already is. Now gently enlarge that picture. Do not jump straight to 16 million yet. Just imagine the Milky Way becoming twice as wide, then 5 times, then 10 times. By that point, our elegant spiral home would already feel almost absurd. But Alcyoneus does not stop there. It keeps going. It moves past 10, past 50, past 100, until the very idea of a galaxy begins to feel less like a structured island of stars and more like a cosmic act of overreach. This is the moment where comparison starts to shift from scale into mood. Because the Milky Way, for all its grandeur, still feels like a home. It feels organized. Spiral. Contained. Large enough to inspire awe, but not so large that the word galaxy breaks apart in your hands. Alcyoneus does something different. It does not simply feel bigger. It feels almost category-breaking. Part of that is because the Milky Way is mostly understood by us as a stellar galaxy, a great disk of stars, gas, dust, and dark matter. Alcyoneus, on the other hand, earns its astonishing size through giant radio lobes powered by the central black hole in its host galaxy. In other words, the part that makes Alcyoneus feel impossible is not a bright disk of ordinary starlight, but an enormous black hole-driven structure seen in radio wavelengths. The discovery paper and Leiden's announcement both emphasize that the record-setting size belongs to the radio structure tied to the galaxy. That detail matters more than it first seems. Because if you compare the Milky Way to Alcyoneus as if both were just ordinary visible disks, you miss the strangeness of what is happening. This is not simply one spiral galaxy outgrowing another. It is more like one galaxy discovering a way to project itself far beyond the visible limits that usually define a galaxy in the popular imagination. And that is why the comparison feels so eerie. The Milky Way is a galaxy you can imagine living inside. Alcyoneus is a galaxy-made structure so extended that it begins to feel less like a place and more like a reach into the intergalactic dark. Another way to feel the scale is to compare Alcyoneus not just to the Milky Way, but to our galactic neighborhood. Andromeda, the Milky Way's nearest major galactic neighbor, lies about 2.5 million light-years away. The local group, the collection of more than 50 nearby galaxies that includes the Milky Way and Andromeda, spans nearly 10 million light-years across according to NASA. That means Alcyoneus, at roughly 16.3 million light-years long, is larger than the entire local group in end-to-end extent. Pause there. Because that is one of those comparisons that changes the emotional texture of the whole story. The Milky Way and Andromeda feel, to us, like major landmarks. They are the great local powers. Around them drift numerous smaller satellite galaxies, all bound into the local group, our immediate extragalactic neighborhood. That neighborhood itself already feels enormous. Nearly 10 million light-years across. A scale so vast it makes the Milky Way seem only one member of a larger family. And yet Alcyoneus exceeds even that. If you placed the host galaxy of Alcyoneus where the Milky Way is, its total end-to-end radio structure would not just reach Andromeda. It would go far beyond it. One half of its full span would extend more than 8 million light-years from the center, enough to carry it beyond the radius of much of the local group itself. That is not just larger than the Milky Way. That is larger than the whole familiar neighborhood that contains the Milky Way. And suddenly the Milky Way changes character in the mind. Not because it becomes less beautiful. Not because it shrinks in any literal sense. But because it is no longer the scale of the story. It becomes one tile in a mosaic that is much larger than we normally allow ourselves to feel. This is the strange gift of cosmic comparison. It does not insult what came before. It simply widens the room around it. There is another way to compare them, one that feels a little more human. The Sun takes about 250 million years to orbit once around the center of the Milky Way. That is one galactic year for us. Dinosaurs appeared and vanished in less than 2 galactic years. Whole chapters of Earth's biological history pass in the time it takes our solar system to make a few circuits of our home galaxy. The Milky Way is already large enough that motion through it becomes almost indistinguishable from stillness on human timescales. Now imagine something more than 100 times larger in overall extent. The word galaxy begins to stop behaving like a geographic term and starts behaving like weather. Like a field. Like an environment that exceeds the normal comfort of boundaries. You no longer think only in terms of stars gathered into a disk. You begin to think in terms of influence, distance, and persistence. And perhaps that is the deepest difference between the Milky Way and Alcyoneus as emotional objects. The Milky Way feels inhabitable. Alcyoneus feels unimaginable. The Milky Way offers structure. It gives us arms, a central bar, star clouds, dust lanes, and a place for the sun to belong. Even its great size still allows for a sense of orientation. We can say where we are, more or less. We are in a barred spiral galaxy, about halfway out from the center, in one small corner of one arm. NASA's Milky Way summaries keep that picture surprisingly grounded. Vast, yes, but still navigable in the mind. Alcyoneus resists that kind of mental orientation. It is too extended, too dependent on radio structures we cannot see with ordinary eyes, too detached from our everyday intuition about what a galaxy is supposed to be. It is not merely a larger home. It is a revelation that the word home was never enough for some galaxies in the first place. And yet there is something soothing in realizing that even these impossible scales can still be related back to familiar ones. You do not have to understand 16 million light-years all at once. You only have to understand the Milky Way. Then you let the Milky Way repeat, again and again and again. That is the rhythm the mind can follow. 1 Milky Way, 10 Milky Ways, 50, 100. Until at some point the imagination gives up trying to picture every detail and simply surrenders to the truth that the universe allows structures far greater than our first instincts would ever permit. Leiden's announcement said that on the sky, Alcyoneus covers an apparent angle comparable to the full moon, despite lying roughly 3 billion light-years away, simply because it is so physically enormous. That is one of those facts that feels almost impossible the first time you hear it. The moon is close, intimate, familiar. Alcyoneus is staggeringly distant. For the two to occupy a roughly similar apparent span in the sky, the physical scale of Alcyoneus has to be almost beyond normal intuition. That comparison is worth savoring because it does something subtle. It takes the giant out of abstraction and places it, softly, back into the sky. Not as something you can directly see with your eyes, but as something that reminds you the sky is full of structures whose true dimensions are hidden behind faintness, wavelength, and distance. Things can appear small and be vast. Things can appear ordinary and be world-breaking. Things can remain invisible for ages, not because they are rare, but because our senses were never enough on their own. And in that sense, comparing Alcyoneus to the Milky Way is not only a lesson in scale, it is also a lesson in humility. Our home galaxy feels immense because it is immense, but it also feels central because it is ours. That is natural. Every creature begins by measuring the universe from the place where it first opened its eyes. The Milky Way is our first cosmic room. It contains the stars our ancestors named, the center our sun orbits, the dust and gas from which our system was born. But Alcyoneus reminds us that our room is not the building, not even close. There are structures so much larger than the Milky Way that our whole local neighborhood can begin to feel like a small district in a city whose full map we still do not understand. If this slow walk-through scale is helping you unwind, and you enjoy these calm comparisons that make the universe feel bigger without shouting about it, a gentle like or subscribe always helps. And if one of these comparisons landed for you, the 100 Milky Ways, the local group, or the moon-sized span in the sky, you can leave that in the comments too. I always like hearing which image makes the scale finally click. For now, let's bring the comparison home one last time. The Milky Way is about 100,000 light-years across in its main disk. It is already vast enough that light needs 100,000 years to cross it, and our Sun needs about 250 million years for one orbit around its center. Alcyoneus, by contrast, was measured in 2022 at about 16.3 million light-years from end to end as a giant radio galaxy structure. That makes it on the order of 100 to more than 150 Milky Ways across, and longer than the entire local group of galaxies that contains the Milky Way and Andromeda. That is the true emotional answer to the comparison. The Milky Way is a giant. Alcyoneus makes giant feel local. And once you feel that, even a little, the next question arrives almost on its own. How does anything become that large? How can a galaxy, especially one whose host is not outrageously unusual in the ordinary visible sense, produce structures that so utterly outscale our home galaxy and even our local neighborhood? That is the deeper mystery waiting just beyond the comparison. Part 7. Why this galaxy became so enormous? Once you hear how large Alcyoneus is, the next question arrives almost by itself. Not what it is, not where it is, but how. How does something like that happen at all? How does a galaxy, especially one whose visible host does not look outrageously special, end up producing a structure so vast that it stretches across about 16.3 million light-years? That is not just a matter of being big. It is a matter of becoming big, and those are not always the same thing. One is a snapshot. The other is a history. And with Alcyoneus, that history is what makes the whole object feel so strange. The 2022 Discovery paper described Alcyoneus as a giant radio galaxy with a projected proper length of 4.99 megaparsecs and noted that, beyond its geometry, both the source and host galaxy appear suspiciously ordinary. That phrase, suspiciously ordinary, is one of my favorite phrases in this whole story, because it tells you, almost immediately, that the old, simple explanation is not enough. If Alcyoneus had turned out to live inside a host galaxy with an absurdly massive black hole, extraordinarily powerful jets, and some impossible abundance of stars and gas, then the mystery would feel simpler. We could say, of course it grew huge. It started huge. But that is not what the researchers found. They reported that Alcyoneus's radioluminosity, stellar mass, and black hole mass were all lower than, though still broadly similar to, those of the median giant radio galaxy in their comparison sample. And that changes the mood of the whole explanation, because it suggests that becoming enormous is not only about raw power. Sometimes it is also about conditions, about time, about resistance, about what is waiting beyond the visible edge of the host galaxy. In a way, Alcyoneus seems to have become gigantic not by being the loudest object in the room, but by having the right conversation with the room around it. To understand that, we have to start at the center. Like many large galaxies, Alcyoneus contains a supermassive black hole. But black holes, despite the drama surrounding them, do not always behave like monsters in a constant frenzy. Much of the time they are quiet. They matter enormously, but they do not always announce themselves. What changes everything is whether enough material falls inward. When gas and other matter spiral toward the black hole, magnetic fields and extreme conditions near the center can help launch jets in opposite directions. Those jets then carry energy and particles far out of the galaxy, inflating giant radio lobes as they plow through the thin material between galaxies. Alcyoneus is a low excitation radio galaxy, which means it is not one of the brightest, most radiatively intense active galaxies, but it still produces the kind of jet-driven structure that can grow into something vast. So one part of the answer is simple in principle. Alcyoneus became enormous because its central black hole launched jets, and those jets kept carving outward for immense stretches of time. But that only pushes the question back a step. Why did those jets manage to get so far? Why did they not stall earlier, or fade sooner, or inflate something more modest? And this is where the surrounding environment becomes just as important as the galaxy itself. The Discovery team pointed to the cosmic web environment around Alcyoneus as a likely clue. Their paper says the source resides in a filament of the cosmic web and may have significant thermodynamic interaction with it. Leiden University's explanation put this more vividly. noting that Alcyoneus inhabits a filament and that its plumes seem to feel a kind of headwind as they move through the medium, subtly shaping their form. In other words, the giant size is not just a story about what the galaxy is doing from the inside out. It is also a story about what the intergalactic environment allows, resists, or guides. This is where the image becomes softer and more beautiful. It is tempting to think of a giant radio galaxy as a pure act of force. A black hole punches outward, and space simply yields. But that is too simple. In reality, the jets have to travel through a medium, however thin. Intergalactic space is not truly empty. It contains extremely diffuse gas, magnetic fields, and the broader structure of the cosmic web. If that environment is denser, rougher, or more confining, the jets may lose momentum sooner, or inflate more compact lobes. If it is less dense, they may travel farther. If the structure of the surrounding filament is favorable, the lobes may expand in ways that let them survive and grow over a much greater scale. The Leiden team explicitly highlighted the surrounding environment as a major focus for explaining Alcyoneus's titanic size because the usual suspects, like an exceptionally massive black hole or unusually powerful jets, did not stand out as the obvious cause. So already, we can begin to sketch a calmer, more believable picture. Not a galaxy that simply won by brute strength, but a galaxy whose jets found room to keep going. Room matters. That may sound almost too gentle for a cosmic explanation, but in astronomy the gentler idea is often the deeper one. A tree does not grow only because it is alive. It also grows because the soil, water, sunlight, and surrounding space let it. Something similar may be true for Alcyoneus. The jets alone are not the full explanation. The universe around the galaxy had to be permissive enough, or at least structured enough, to let those jets inflate lobes on an almost absurd scale. That is partly why the discovery paper emphasized thermodynamic interaction with the cosmic web environment and record low lobe pressures. That detail about pressure is especially important. The researchers found that the lobes of Alcyoneus have extraordinarily low pressure, the lowest yet found at the time in such a system. This matters because pressure tells you something about the state of the lobes and how they are interacting with the medium around them. Very low pressure lobes suggest structures that have expanded a great deal into a very tenuous environment. They are not cramped. They are not tightly confined. They are diffuse, extended, and in that sense almost fragile, even while being enormous. The authors described Alcyoneus as one of the most promising radio galaxies for probing the warm hot intergalactic medium precisely because of those low lobe pressures. There is something almost haunting in that idea. The giant is not dense and heavy in the way people often imagine giant things to be. It is immense partly because it is diffuse. It reaches so far not by becoming thicker and more solid, but by stretching farther into a thin and forgiving environment. That makes Alcyoneus feel less like a brute and more like a breath. A long, ancient breath pushed outward by a black hole and preserved by space. And that leads to another likely piece of the puzzle: time. Even if the jets are not unusually powerful, and even if the host galaxy is not freakishly massive, a structure can still become enormous if the jet activity persists long enough, or if the lobes remain visible and coherent long enough to keep expanding. The discovery paper does not claim a single settled age scenario for Alcyoneus, but giant radio galaxies in general are understood as systems whose structures have had time to grow to megaparsec scales. Inference-wise, that means duration matters almost as much as power. A modest but sustained process can sometimes outrun a violent but shorter-lived one. That is not stated as the only explanation in the Alcyoneus paper, but it follows naturally from the physics of giant radio galaxy growth and the paper's emphasis on ordinary host properties plus extreme geometry. And that is a strangely comforting kind of explanation. Not sudden greatness. Sustained greatness. Not a single outburst. a long persistence. In this way, Alcyoneus almost feels more understandable. You do not have to imagine an impossible galaxy doing impossible things all at once. You can instead imagine a galaxy that had enough energy, enough time, and just enough environmental permission to keep extending its influence long after many others would have stopped. In science, that kind of explanation is often more satisfying than the dramatic one, because it tells us the universe may make giants through patience as well as violence. There is also another subtle point hidden in the discovery. The host galaxy of Alcyoneus is not sitting in the crowded center of a rich cluster in the way some massive visible giant ellipticals do. The nearest cluster mentioned in summaries of the source is not right on top of it, and the source instead appears associated with a filamentary cosmic web environment. That relative environmental context may matter greatly, because it changes what the jets have to travel through. Dense cluster centers can be powerful places, but they also mean more surrounding material, more pressure, more interaction. A quieter large-scale environment may allow radio lobes to grow farther before they dissipate. The discovery team did not frame this as a final proven answer, but it is one of the main reasons they saw the environment as crucial to understanding the source. This is one of those places where it helps to be honest about uncertainty. Astronomers do not fully know, in one final and settled sense, why Alcyoneus became as large as it did. That is not a flaw in the story. It is the story. The mystery remains partly open. The 2022 paper presented Alcyoneus not just as a record holder, but as a clue, a giant example that could help scientists learn what really drives radio galaxy growth. The fact that the host seemed ordinary was not the end of the explanation. It was the beginning of a better question. And that may be what makes Alcyoneus so scientifically valuable. If it had been easy to explain, it would still be beautiful, but it would be less useful. The universe becomes especially interesting when it gives us an extreme example that does not match our first expectations. Alcyoneus seems to say that giant size does not require the most massive black hole, or the most luminous radio power, or the most exaggerated host galaxy. Instead, giant size may emerge from a more delicate combination of ingredients: a capable central engine, long-lived jet activity, very low surrounding resistance, and a position in the cosmic web that lets the plumes keep going. That is an inference from the sources rather than a single direct quote, but it is the clearest way to summarize what astronomers currently see as the leading explanation. In other words, the galaxy became enormous because the universe let it. That is not the whole answer, but it may be the most human-sounding version of it. We sometimes think of scale as a measure of ambition, as if bigger things simply wanted more. But astronomy often teaches a quieter lesson. Things become immense when conditions align. Growth is not only about the engine, it is also about the medium, the path, and the time available to continue. And in that sense, Alcyoneus is almost more elegant than a visibly overpowered giant would have been. Its greatness is not blunt. It is negotiated. It is shaped by a conversation between the black hole and the cosmic web, between pressure inside the lobes and pressure outside them, between persistence and permission. That is why the Leiden statement's image of the plumes, dancing with an invisible partner, is so striking. It captures the idea that the radio structure is not simply imposing itself on the universe, but being shaped in return by the universe it moves through. And now the whole object feels different, less like a cosmic accident, more like a revelation of process. The giant did not appear from nowhere. It grew along the pathways the universe made possible for it. If this gentle kind of science storytelling is helping you settle in, you can leave a quiet like, subscribe for more of these long cosmic journeys, or tell me in the comments which explanation fascinates you most: the black hole at the center, the role of time, or the invisible environment around the galaxy. I always like seeing which part of the universe people feel most drawn to. For now, though, let us gather the thread of the story. Alcyoneus seems to have become so enormous not because its host galaxy is outrageously exceptional in every ordinary way, but because it combined an active central engine with a surrounding environment that may have offered unusually low resistance and strong interaction with a cosmic web filament. Its lobes show extremely low pressure. Its host appears comparatively ordinary for such an extreme giant radio galaxy, and that combination is exactly what makes it such an important object for astronomers trying to understand how radio galaxies grow to megaparsec scales. That is the best answer we have right now. Not one dramatic cause, but a subtle alignment of causes. A black hole that could launch, a structure that could endure, an environment that did not shut the process down too early, and enough time for all of it to stretch into something that now feels almost mythological when we measure it from Earth. Once you see that, Alcyoneus becomes more than a record holder. It becomes a lesson in how the biggest things in the universe are often not simply the most violent or the most massive. Sometimes they are the things that found the least resistance and kept going. And that idea carries us naturally into the next part of the story. Because if the surrounding environment helped make Alcyoneus what it is, then we need to step back even farther and ask what kind of environment that really was. What sort of cosmic landscape allows a galaxy to grow structures on this scale? That is where the quiet architecture of the cosmic web begins to matter. Part 8: The quiet cosmic environment around it. By this point in the story, the black hole at the center of Alcyoneus no longer feels like the whole explanation. It matters, of course. Without that central engine, there are no jets, no lobes, no giant radio structure stretching across millions of light years. But Part 7 leaves us with a quieter truth. The engine alone is not enough. To understand why Alcyoneus became so enormous, we have to step back from the galaxy itself and look at the larger landscape it lives inside. And when we do that, the picture becomes even more beautiful. Because galaxies are not scattered randomly through the universe like dust in an empty room. On the largest scales, NASA describes the universe as a cosmic web, a vast large-scale structure made of twisting, thread-like filaments, concentrations like clusters and walls, and the voids between them. Hubble's science pages describe this web as an interconnected pattern of filaments and sheets, largely shaped by dark matter and gravity over cosmic time. That phrase, cosmic web, is one of those rare scientific terms that sounds almost too poetic, and yet it turns out to be exactly right. The universe, when viewed on the largest scales, does not look like a random spray of galaxies. It looks structured. Filaments stretch across space like threads. Clusters gather where those threads intersect. Vast emptier regions, the voids, lie between them. NASA even describes the web as a kind of scaffolding that cradles everything that exists within the universe. And once you know that, Alcyoneus starts to feel less like an isolated mystery and more like part of a landscape. The 2022 Discovery paper says Alcyoneus most probably inhabits a filament of the cosmic web, and a low-density environment remains a possible explanation for its formidable size. Another summary of the same work notes that although it lies on the high end of the density distribution, it is still outside a cluster and most likely in a filament rather than a rich cluster core. That distinction may sound small, but it changes everything. A galaxy sitting deep inside a dense cluster lives in a rough neighborhood. The space between galaxies in a cluster is not empty. It contains hot gas, pressure, motion, and a lot of opportunities for jets and lobes to be disrupted, confined, or bent back. A filament, by contrast, is still part of the web, still structured, still full of matter on cosmic scales, but it can be a quieter corridor. Not empty, just gentler. Not nothing, but less crowded. NASA's overview of large-scale structure and Hubble's cosmic web explanations both emphasize that filaments connect larger concentrations while voids open between them, giving the universe a kind of threaded architecture rather than a uniform one. And this is where Alcyoneus begins to feel almost less like a giant beast and more like a traveler that found the right road. If the jets from its central black hole were moving out into a filament rather than fighting through the denser chaos of a cluster center, then they may simply have had more room to grow. More room, more time, less resistance. The discovery paper is careful here. It does not claim one final answer, but it does explicitly say a low-density environment remains a possible explanation for the source's huge size. There is something deeply calming in that idea. The giant did not become a giant only because it pushed hard. It also became a giant because the universe around it did not stop it too soon. Leiden University's summary of the discovery makes this even more vivid. It says Alcyoneus's plumes may reveal information about the elusive filaments of the cosmic web, and that because Alcyoneus inhabits a filament, its plumes feel a kind of headwind as they move through the medium. That headwind subtly changes their direction and shape, leading the researchers to describe the plumes as performing a slow dance with an invisible partner. That image is almost impossible to forget once you hear it. A slow dance with an invisible partner. Not an explosion into nothingness, but a long negotiation with a medium we usually cannot see. And that is important, because it reminds us that intergalactic space is not truly blank. The medium in filaments may be very thin, very difficult to detect, but it is there. Hubble's cosmic web pages describe filaments as structures where matter exists between galaxies, and NASA's large-scale structure pages describe the bright knots of galaxies connected by strands of material. So when the jets of Alcyoneus push outward, they are not crossing a perfect vacuum. They are moving through a subtle environment, one delicate enough to hide from easy observation, but real enough to shape the lobes over millions of years. Leiden's write-up says the plumes are so big and rarefied that the surrounding medium can relatively easily mold them. And that is where the whole story becomes almost strangely tender. Because the largest known galactic origin structure of its time was not only made by force, it was also shaped by softness. The lobes of Alcyoneus are not great iron beams driven through rigid space. They are diffuse, rarefied structures, so extended and delicate that the medium around them can gently steer them. That matches the discovery paper's finding that the pressures in the lobes are the lowest yet found at the time. In other words, these giant lobes are not just large. They are also unusually low pressure, and that makes them especially sensitive to their surroundings. That low pressure is one of the most scientifically important parts of the whole system. Because if the lobes are so diffuse and under such low pressure, then they become a kind of tool, a probe. The paper says Alcyoneus therefore represents one of the most promising radio galaxies yet to probe the warm hot intergalactic medium, often shortened to WIM. That medium is thought to occupy parts of the cosmic web and has long been difficult to study directly. This is one of those quiet moments where a giant object becomes useful for something even bigger than itself. Alcyoneus is not only a record holder. It is a way of feeling the cosmic web. Usually, we can see the galaxies in a filament much more easily than the medium between them. The galaxies are the lanterns. The filamentary gas is more like breath on cold glass, hard to catch, easy to miss. But a giant radio galaxy like Alcyoneus can interact with that medium so strongly, and over such a large distance, that its lobes become a visible response to an otherwise elusive environment. Leiden's announcement says researchers had long proposed that the shapes and pressures of radio galaxy plumes could relate to filament properties, and that Alcyoneus offered one of the most plausible cases yet for that connection. So now the environment around Alcyoneus begins to feel like more than background. It becomes a co-author. The black hole launches the jets, yes, but the filament helps determine how that story unfolds. The surrounding medium shapes the lobes, influences their pressures, and may have provided exactly the kind of corridor in which something so extended could survive and keep growing. The discovery papers focus on thermodynamic interaction with the cosmic web. Filament points directly in that direction. And there is something almost philosophical in that. We often imagine greatness as a private achievement, as though the largest things simply overpower the world around them. But astronomy keeps offering gentler lessons. Sometimes the largest things are not only the ones with the strongest engine. Sometimes they are the ones whose environment quietly allowed them to keep going. That may be exactly what happened here. Alcyoneus seems to sit in a place that is structured enough to belong to the cosmic web, but not so dense that the growing lobes were crushed or stalled too quickly. It may be, in a sense, living on a long road rather than in a crowded square. That is an inference from the discovery team's discussion of the filament environment and low-density explanation, but it is the clearest beginner-friendly way to picture the situation. And once you picture it that way, the giant becomes easier to understand. Not easy, exactly, but gentler. Imagine smoke drifting through a narrow, steady valley instead of slamming into a city full of walls. Imagine a river allowed to keep widening because the land around it falls away rather than forcing it into a tight channel. Those are not perfect scientific models, of course, but they capture something emotionally true about the difference between a permissive environment and a hostile one. The cosmic web is not scenery. It is part of the mechanism. That is one reason NASA and Hubble both present the web not as an optional add-on to cosmic structure, but as the backbone or scaffolding of the universe on large scales. Galaxies, clusters, and filaments are all parts of one larger architecture. Alcyoneus is not floating free of that architecture. It is embedded in it, and its giant size may be one of the most dramatic examples of how a galaxy and the web around it can shape one another. Leiden's summary goes even a step further and suggests that central black holes in galaxies may help keep the cosmic web warm through what their jets transport outward. It compares the scale mismatch almost humorously, like something the size of a marble helping regulate the Earth's temperature. Whether or not that exact analogy stays with you, the underlying point is remarkable. A black hole tiny by cosmic web standards can still feed energy into the much larger structure around it. So the relationship runs both ways. The filament may have helped Alcyoneus grow. And Alcyoneus, through its jets and lobes, may have pushed energy back into the filament. That is not a one-way story. That is an exchange. And maybe that exchange is the real emotional center of Part 8. Because by now Alcyoneus no longer feels like a lonely giant. It feels connected, suspended in a network, influenced by a wider structure, while also influencing it in return. That is a more mature picture of the universe than the older, simpler one where galaxies seem like isolated islands. NASA's and Hubble's descriptions of the cosmic web both make clear that galaxies live in a connected large-scale pattern, not in splendid isolation. If this calm walk through the cosmic web is helping you unwind, a gentle like or subscribe is always appreciated. And if there is a single image from this section that stays with you, the scaffolding, the invisible headwind, or the slow dance with an invisible partner, you can leave that in the comments. For now, let's gather the thread. The quiet cosmic environment around Alcyoneus matters because the galaxy appears to live in a filament of the cosmic web rather than deep inside a rich cluster, and the discovery team specifically identified a low-density environment as a plausible reason its giant radio structure could grow so large. Its plumes seem sensitive to the surrounding medium, its lobes have extraordinarily low pressure, and those properties make the system one of the best-known opportunities to use a giant radio galaxy to probe the warm hot intergalactic medium in the cosmic web. That is the quiet architecture behind the giant. Not empty space, but structured space. Not isolation, but context. Not just a black hole shouting into the dark, but a galaxy and a filament shaping one another over immense time. And once you see that, Alcyoneus starts to feel less like a freak exception and more like a clue. a clue that the biggest galactic structures may tell us as much about the invisible universe around galaxies as they do about the galaxies themselves. Which leads naturally to the next question. If a structure this large could hide in radio data until recently, could there be even bigger galaxies, or galaxy-made structures, still waiting in the dark for us to find them? Part 9. Could there be even bigger galaxies we haven't seen yet? After meeting Alcyoneus, it is almost impossible not to ask the next question. Is that really the end of the story? Did we finally find the ultimate giant, the last word in galactic size, the record that will stand quietly forever? Or are we still early in this search, still wandering through a universe that has not yet shown us its true extremes? The honest answer is the most beautiful one. Yes, there could absolutely be even bigger galaxies, or at least bigger structures made by galaxies, still waiting to be found. And in one important sense, that has already happened. In 2024, astronomers reported Porphyrion, a black hole jet system spanning about 7 megaparsecs, or roughly 23 million light-years, making it the largest pair of black hole jets yet observed and larger than Alcyoneus in total extent. The discovery team described it as a structure on the scale of the cosmic web itself. That changes the emotional tone of the whole question, because it means Alcyoneus was never the endpoint. It was a threshold, a revelation, a moment when astronomers realized the old picture was too small. And then, almost immediately in cosmic terms, the universe answered back with something larger still. Porphyrion did not cancel Alcyoneus. It confirmed the deeper lesson Alcyoneus had already begun to teach us, which is that our previous sense of galactic scale had probably been too conservative, especially when it came to giant radio structures. And once you accept that, a quieter possibility opens up. If one record could be overturned so soon, then perhaps the real frontier is not a single champion, but a hidden population of giants we have only just begun to notice. That idea is strongly supported by recent survey work. A 2025 astronomy and astrophysics study compiled an unprecedented sample of 143 giant radio galaxies larger than 3 megaparsecs, including 69 newly found by the authors, and reported 6 examples clearly exceeding 5 megaparsecs, reaching up to 6 megaparsecs. That is an important shift. It suggests the extreme end of the giant radio galaxy population is no longer just a lonely curiosity. It is becoming a real landscape of objects. And then there is the matter of the surveys themselves. Every time radio astronomy becomes more sensitive, the universe seems to grow new limbs. In 2026, the LOFAR collaboration released the most detailed radio map of the universe yet made, cataloging about 7 million cosmic radio sources. Official summaries of that release emphasized that it provides the most complete census yet of actively growing supermassive black holes and showcases radio emission extending for millions of light years. A map like that is not just a catalog. It is a promise. It means astronomers are looking at a vastly larger pool of possible giant structures than ever before. And that matters because giant radio galaxies are especially easy to underestimate. Not because astronomers are careless, but because these structures are often faint, diffuse, and easy to miss. Their brightest host galaxy may be obvious, while their most extended outer lobes sit almost invisibly in the radio background. The 2022 Alcyoneus work itself came from reprocessing radio data to make weaker structures stand out more clearly. More recent survey papers reinforce the same theme. A 2025 ASKAP study reported 15 new giant radio galaxies in one wide-field survey region and found dozens more extended radio galaxies, showing again how improved wide-field, low-surface brightness imaging keeps revealing giants that were previously overlooked. So when we ask whether something bigger may still be out there, we are not asking a romantic question in defiance of the evidence. We are asking the question the evidence seems to encourage. Because what the evidence keeps showing is that the known population of giant radio galaxies has been shaped, in part, by the limitations of older instruments and older surveys. Better sensitivity, wider sky coverage, and improved image processing do not just refine the list. They expand it. They make the universe less finished than it looked a few years earlier. There is also another reason to suspect bigger objects may still be waiting. The known giants do not all live in the same kind of environment. Some seem to inhabit relatively sparse or filamentary regions of the cosmic web, where lower surrounding density may allow jets and lobes to keep growing. Others show environmental interactions that shape or bend them. The 2025 study of giant radio galaxies larger than 3 megaparsecs found that only a minority are clearly associated with clusters, and that bending angles are larger for those in clusters than for those not associated with clusters. In simple terms, the environments that most favor extreme growth may not be the ones astronomers once paid the most attention to. The biggest structures may prefer quieter corridors, not the most crowded cosmic city centers. And that thought is strangely calming, because it means the biggest things in the universe may not always announce themselves from the busiest places. They may grow in silence. They may stretch outward in thinner regions, along filaments, in corners of the radio sky where no one had yet looked deeply enough. A giant can hide, not because it is rare in principle, but because it is faint in the wrong wavelength and patient on the wrong timescale. Alcyoneus taught that lesson clearly, and Porphyrion deepened it. Now, it is worth being precise here. If by bigger galaxy, you mean a larger visible body of stars, then the answer becomes more cautious. Giant visible stellar systems like the old record holders remain extraordinary, and they are shaped by long histories of mergers, cannibalism, and cluster growth. It is certainly possible that an even more extended stellar giant exists and has not yet been recognized in full, especially if its faint outer halo has not been measured deeply enough. But the recent evidence is strongest on the radio side of the story. That is where the frontier is clearly moving, and that is where the biggest surprises have arrived. So perhaps the best answer is this. Yes, bigger structures almost certainly remain to be found, especially among giant radio galaxies and black hole jet systems. Not because astronomers are guessing wildly, but because new surveys are still uncovering new giants. The known sample of extreme giant radio galaxies has grown sharply, and recent discoveries have already pushed the record beyond Alcyoneus. When a field is still expanding this quickly, it is usually a sign that the sky contains more than our catalogs yet admit. There is something lovely about that. The universe has not run out of room to surprise us. Even now, with all our telescopes and maps and patient mathematics, we are still finding structures that force us to redraw the scale of what a single galaxy can do. We are still learning that a galaxy is not just its stars. It is also its reach, its black hole, its environment, its age, its radio whisper stretched almost beyond comprehension. And maybe that is the gentlest truth in all of this. The question, what is the largest galaxy ever observed, sounds like it wants an ending, a final answer, a clean crown. But the cosmos does not seem interested in endings. It keeps turning every answer into a doorway. Alcyoneus was a doorway. Porphyrion was another. And somewhere in the radio dark, beyond the current limits of our surveys, there may already be something larger still, waiting patiently for us to learn how to see it. If this slow journey through the biggest structures in the universe is helping you unwind, you can softly subscribe, leave a like, or share in the comments whether you think the true giants of the cosmos are the visible ones full of stars, or the hidden radio giants we only meet through better instruments. And now the story is ready for its final turn. Because once we admit that the record may keep moving, the most interesting question is no longer just which galaxy is biggest. It becomes what these giants are trying to teach us about the universe itself. Part 10. What the largest galaxy teaches us about the universe. At the beginning of this journey, the question sounded so simple. What is the largest galaxy ever observed? It felt like the kind of question that should have one clean answer waiting at the end. One name, one object, one final giant standing alone above all the others. But by the time we followed the story through visible stellar giants, faint outer halos, black hole jets, radio lobes, and the quiet scaffolding of the cosmic web, the question had changed. It had become less like a record book entry and more like a mirror. Because what we found was not only a giant galaxy, or a giant galactic structure. We found a different way of seeing the universe itself. And maybe that is the most satisfying ending this story could have. Not a perfectly tidy answer, but a larger understanding. Because the biggest lesson is this: the universe is under no obligation to fit inside our first definition of a thing. We like categories that behave. We like edges, rankings, labels, and tidy comparisons. We want a galaxy to feel like an island of stars with a measurable width and a clear border. But the real universe keeps resisting that simplicity. A galaxy can be a city of stars, yes, but it can also be a vast dark matter halo. It can be a long history of mergers. It can be a central black hole powerful enough to launch structures across millions of light years. It can be all of those things at once, and depending on which of those faces we choose to measure, the largest galaxy can mean something very different. That may sound like a complication, but it is really a kind of deepening. In ordinary life, when something becomes harder to define, we often feel frustrated. In science, that difficulty can be a sign that we are finally touching the real shape of things. The galaxy was never smaller than our first definition. Our definition was simply narrower than the galaxy. That is what objects like Alcyoneus revealed so beautifully. In 2022, astronomers reported Alcyoneus as a giant radio galaxy with a projected length of about 4.99 megaparsecs, or roughly 16.3 million light-years, and they described it as the largest known structure of galactic origin at the time. Just as importantly, they noted that the host galaxy itself seemed suspiciously ordinary compared with the extreme scale of the radio structure. That detail matters because it changes the whole emotional logic of the story. It tells us that the universe does not reserve its greatest surprises only for the most obvious places. The largest visible body of stars is one kind of giant. But sometimes the more astonishing giant hides in a structure we cannot see in ordinary light at all. Sometimes the galaxy that changes the conversation is not the brightest or the most visibly dramatic one. Sometimes it is the one whose black hole, over immense time, quietly pushes its influence farther into the dark than anyone expected. And then, just when that felt almost enough, the universe widened again. In 2024, astronomers reported Porphyrion, a black hole jet system spanning about 7 megaparsecs, or roughly 23 million light-years, even larger than Alcyoneus in overall extent. Caltech described it as the biggest pair of black hole jets yet seen. Nature described those jets as the biggest yet discovered. In other words, even after Alcyoneus had already expanded our imagination, the sky still held something larger. And that is lesson number 2. The universe is not finished with our sense of scale. There is something wonderfully destabilizing about that. It means the biggest thing we know is rarely the biggest thing that can exist. It is only the biggest thing we have recognized so far, using the tools and definitions available at that moment. When instruments improve, when surveys grow wider and deeper, when astronomers learn how to notice fainter radio structures, the map changes. That is not a failure of science. That is science doing exactly what it should do. The known universe becomes larger not because the cosmos itself changes, but because our attention becomes more sensitive. The 2025 Giant Radio Galaxy study that assembled 143 systems larger than 3 megaparsecs shows that these giants are not just isolated accidents. They are a growing population that has become easier to see as radio astronomy improves. There is a kind of comfort in that. It means reality is richer than our current catalog. It means mystery is not a temporary embarrassment waiting to be cleaned up. It is part of the natural atmosphere of discovery. And then there is the black hole. If there is one idea that keeps returning in this story like a quiet pulse, it is that black holes are not merely destroyers. In the public imagination, black holes are often treated as cosmic endings, dark mouths that swallow matter and erase it from the visible world. But the largest galactic origin structures remind us that black holes can also be engines of distribution. Through jets, they can move energy outward on staggering scales. The giant structures associated with Alcyoneus and Porphyrion show that a galaxy's central black hole can affect regions millions of light-years away, on scales approaching those of the cosmic web itself. Caltech's summary of Porphyrion emphasized precisely this, arguing that giant jet systems may influence the formation of galaxies in the young universe and help spread magnetism through the cosmos. That should change how we feel about the centers of galaxies. Not because it makes them less strange, but because it makes them more creative. The black hole is not only a sink. Under the right conditions, it becomes part of a feedback loop with the wider universe. Matter falls inward, but energy goes outward. The galaxy and its environment begin to shape each other. That is especially clear in Alcyoneus, where the discovery team argued that the source resides in a filament of the cosmic web and may have significant thermodynamic interaction with it, while the very low pressures in its lobes make it an unusually promising probe of the warm-hot intergalactic medium. And that brings us to another major lesson. Nothing in the universe is as isolated as it first appears. A galaxy can feel like an island when you see it in a beautiful image, a self-contained swirl of stars floating in blackness. But on the largest scales, galaxies are part of the cosmic web, a structure NASA describes as twisting, thread-like filaments connecting groups, clusters, superclusters, and walls, with voids in between. Hubble's cosmic web mapping pages describe the same large-scale structure as an interconnected web of filaments and sheets. Alcyoneus matters partly because its giant radio structure may reveal the properties of the web around it. In other words, the galaxy is not merely sitting in space. It is participating in a much larger architecture. That is one of the most beautiful truths in modern astronomy. The largest galaxy is never only about itself. It is also about the environment that lets it grow, about the medium that shapes its lobes, about the filament that guides or resists its expansion, about the hidden structure around it that does not shine the way stars shine, but still matters profoundly. In this sense, asking about the largest galaxy teaches us to stop treating cosmic objects like isolated trophies. The real story is relational. A giant becomes giant through a conversation with its surroundings, sometimes through mergers, sometimes through long-lived jet activity, sometimes through lower-density environments that allow structures to keep growing, sometimes through a combination of all of these. The largest thing in the sky is often also evidence of the quietest conditions around it. There is another lesson here too, and it may be the most human one. Perspective changes everything. When we compared Alcyoneus to the Milky Way, the giant suddenly became emotionally real. The Milky Way is about 100,000 light-years across, already so large that light takes 100,000 years to cross it. Alcyoneus, at roughly 16.3 million light-years, exceeds that by well over 100 times in overall extent. Porphyrion, at roughly 23 million light-years, stretches farther still. But perhaps the deepest shift is not in the arithmetic. It is in what the arithmetic does to us. It takes the Milky Way, which already feels immeasurable, and turns it into a unit. It reminds us that even our home galaxy is not the scale of the universe. It is only one familiar room inside a structure vastly larger than our instincts can comfortably hold. That can sound intimidating, but it does not have to be. Sometimes people assume that cosmic scale makes human life feel smaller in a cruel way, as though the lesson of astronomy is always that we do not matter. But I do not think that is the deepest reading. The larger lesson is not that we are meaningless. It is that meaning does not depend on being large. Our species is physically tiny beside galaxies, yes. And yet we are the creatures who noticed them. We are the creatures who learned how to infer their distances, compare their sizes, map the cosmic web, and detect faint radio lobes from billions of light years away. In a universe this vast, the fact that matter arranged itself into beings capable of understanding scale at all is not trivial. It is one of the most astonishing things in the story. And that returns us to the original question one last time. What is the largest galaxy ever observed? If you insist on one single neat answer, the truth remains slippery. If you mean the largest visible stellar giant, you may lean toward the old colossal ellipticals. If you mean the largest galactic origin radio structure, Alcyoneus once held that title, and Porphyrion has since surpassed it in jet extent. If you mean something else again, the answer may shift with the definition. But maybe by now that slipperiness no longer feels disappointing. Maybe it feels right. Because the question did exactly what the best scientific questions do. It began with curiosity and ended by enlarging the meaning of its own terms. So what does the largest galaxy teach us? It teaches us that the universe is layered. That starlight is only one version of reality. That black holes can build as well as consume. That the cosmic web is not just scenery, but structure. That record holders are often temporary, because discovery is still alive. And that the biggest things we know are often invitations, not conclusions. It also teaches patience. Because nothing about these giants is rushed. The stars gathered slowly. The black holes fed slowly. The jets inflated slowly. The lobes expanded for ages. The light traveled for billions of years. And the understanding came slowly too, through one telescope, then another, then better maps, then quieter data processing, then a deeper question. In a world that often feels hurried, there is something deeply restful about that. The greatest structures in the cosmos are not products of panic. They are the result of time given room to work. And maybe that is the softest lesson to end on. The universe is large beyond comfort, yes. Strange beyond easy intuition, yes. But it is also patient. It does not demand that we understand everything at once. It lets us approach by degrees. First the stars, then the halo, then the jets, then the filament, then the larger structure behind the structure. That is how real understanding often arrives. Not as a flash, but as a widening. So perhaps the final answer is not a name. Not IC 1101. Not Alcyoneus. Not Porphyrion. Perhaps the final answer is that the largest galaxy teaches us how to look past the obvious light, to look past the first definition, to look long enough that the universe has time to become stranger than we expected, and in becoming stranger, more beautiful. If this calm exploration of the cosmos has been a good companion for your evening, a quiet subscribe or a gentle like always helps. And if you feel like sharing a thought, I'd love to know this. When you think about the biggest structures in the universe, does it make you feel smaller, or does it make the universe feel more like home? Either answer is understandable. Because maybe that is what the largest galaxy really gives us in the end. Not certainty, but perspective. And sometimes, perspective is the most peaceful thing of all.